What if everything we think we know about ancient technology is only a fraction of the truth? Picture a world thousands of years ago. No electricity, no digital networks, no industrial manufacturing, yet somehow, brilliant minds were constructing machines of such staggering complexity that we are only beginning to grasp their purpose and power. These were not simple tools or crude inventions. They were masterpieces of engineering, designed with a sophistication that seems to defy the very timeline of human progress. We often imagine antiquity through a lens of simplicity, but hidden within the dust of history are artifacts so advanced, so precise, that they whisper secrets we are still straining to hear. This isn't just about history, it's about mystery, the kind that pulls at the edges of our understanding and invites us to look deeper. Today, we embark on a journey to explore 28 such wonders, devices crafted with a visionary insight that feels almost out of place in their eras. Think of the Antikythera Mechanism, an ancient Greek astronomical calculator that could predict celestial movements with jaw-dropping accuracy, or intricate water clocks from the Islamic Golden Age that not only told time but modeled the cosmos. These were not isolated flashes of genius. They were part of a tapestry of innovation stretching across civilizations, from elaborate geared systems in China to acoustically perfect temples in the Americas that amplified sound in ways we can barely replicate today. Each device tells a story not just of intelligence, but of ambition, of humans striving to measure, understand, and even master the world around them long before the advent of what we call modern science. What's truly captivating is how these inventions challenge the narrative of linear progress. We often assume that technology evolves in a straight line, each generation building on the last. But these artifacts suggest something far more intriguing. That knowledge has been lost, rediscovered, and sometimes forgotten again in cycles we are only beginning to map. They raise profound questions. How did they achieve such precision without the tools we take for granted? What kind of world did they see that we have missed? And what can these ancient marvels teach us about creativity, curiosity, and the unyielding human spirit? As we uncover the truths behind what these devices really measured, from the passage of stars to the flow of time itself, you may find yourself not only amazed by the past but inspired about the future. This is a voyage into the heart of human ingenuity, and it's one you won't want to miss. Let's begin our journey with perhaps the most famous and mind-boggling of all ancient devices, the Antikythera Mechanism. Discovered by sponge divers in 1901 off the coast of a small Greek island, this corroded lump of bronze and wood lay unnoticed for decades, its true nature completely obscured by centuries of undersea incrustation. It wasn't until the 1970s that advanced imaging technology like X-rays and CT scans began to reveal the breathtaking truth. Inside was an incredibly sophisticated clockwork universe of interlocking bronze gears, precisely cut dials, and intricate inscriptions. This wasn't a simple statue or a piece of cargo. It was a machine of staggering intellect, a mechanical computer built over 2,000 years ago. The purpose of this device was nothing short of monumental. It was a portable cosmos designed to calculate and display the complex movements of the heavens with a level of accuracy that would not be seen again for over a millennium. By turning a hand crank on its side, the user could advance or reverse time, watching as a series of dials and pointers simulated the positions of the sun, the moon, and the 5 planets known to the ancient Greeks. It could predict lunar and solar eclipses years in advance, not just telling you when one would occur, but but the exact hour, the direction it would appear in the sky, and even the color and magnitude of the event details that were deeply tied to omens and portents in the ancient world. But its function went far beyond pure astronomy. One of its dials was specifically dedicated to tracking the 4-year cycle of the ancient Olympic Games and other major Panhellenic festivals, turning it into a social and cultural calendar of immense importance. Another series of gears modeled the irregular orbit of the moon with a brilliant pin and slot mechanism that accounted for its varying speed, a concept of elliptical motion we wouldn't mathematically formalize until Johannes Kepler in the 17th century. It essentially condensed an entire library of astronomical knowledge and complex mathematical calculations into an elegantly engineered box that could be held in your hands. The existence of such a device completely shatters our conventional timeline of technological history. We are left to wonder who built this. For whom was it made? Was it a unique demonstrator model, a philosopher's teaching tool, or was it one of many such devices, a product of a wider tradition of high Hellenistic engineering that was ultimately lost in the fires of war and the collapse of empires? The Antikythera Mechanism stands as a powerful, tangible reminder that the past may have been far more sophisticated than we ever dared to imagine, and its silent, gear-driven poetry continues to measure not just celestial cycles, but the vast depths of our own curiosity. From the intricate celestial gears of ancient Greece, we now travel east to the deserts of Mesopotamia, where another artifact of profound mystery was unearthed. In 1936, just outside the bustling modern capital of Baghdad, workers constructing a railway stumbled upon an ancient tomb. Among the typical finds of pottery and glassware was a collection of objects that seemed utterly out of place, a series of small, unassuming clay jars. Each one, roughly the size of a man's fist, contained a rolled-up copper sheet housing a single iron rod. The jar's top was sealed with asphalt or bitumen, a naturally occurring tar, which also held the iron rod perfectly in place, insulating it from the copper cylinder. To the untrained eye, it was just more ancient junk, but to a curious German archaeologist named Wilhelm Koenig, it looked like something else entirely. It looked, against all logic and history, like a battery, dating from the Parthian period, sometime between 200 years before the Common Era and 200 after. This so-called Baghdad Battery presents a riddle that has divided experts for decades. The components are simple, yet their assembly is tantalizingly specific. If you were to fill such a jar with an acidic liquid, something readily available like vinegar or grape juice, a fascinating reaction would occur. The acidic electrolyte would interact with the two different metals, the copper and the iron, initiating a chemical process that pushes electrons from one to the other. In essence, this creates a flow of electric current, a small but measurable voltage between the two metal terminals. Replicas built based on the original design have consistently produced just over 1 volt of electricity. It's not enough to power a city, but it is enough to make you question everything. So what could this subtle, invisible force have been used for? The most compelling theory points to electroplating, the process of using an electric current to bond a thin layer of a precious metal, like gold, onto the surface of a less valuable object like silver or copper. Artisans across the ancient world were masters of gilding, often using toxic mercury to adhere gold leaf. A small electrical current would offer a far cleaner, more controlled, and potentially more brilliant method, explaining the exquisite gold-covered artifacts found throughout the region. Other theories suggest a more mystical application. Perhaps the gentle tingle from the battery was used in religious ceremonies, a literal shock of the divine administered by priests to astonished worshippers. There's even speculation about medical use, a primitive form of electrotherapy to numb pain or treat ailments, concepts we wouldn't rediscover until centuries later. Of course, skepticism exists. Some argue the jars were simply a secure method for storing sacred scrolls, with the iron rod acting as a core and the asphalt providing a waterproof seal. Yet, no traces of parchment or papyrus have ever been found inside them. The very fact that the debate continues is what makes the Baghdad Battery so utterly captivating. It may not have been a power source as we understand it today, but its existence forces us to confront a powerful idea. It suggests that the spark of electrical discovery was not first struck by Alessandro Volta in the year 1800, but may have flickered quietly in the workshops and temples of an ancient civilization, a lost thread of knowledge measuring not just voltage, but the boundless and often unconventional creativity of the human mind. Leaving behind the enigmatic spark of potential ancient electricity, we now venture into the realm of the completely inscrutable, a puzzle made not of gears or jars, but of symbols. Our journey takes us to the sun-drenched island of Crete, to the magnificent Bronze Age palace of Feistos. It was here in the summer of 1908, during an excavation of a ruined chamber, that Italian archaeologist Luigi Pernia made a find that would become one of archaeology's most enduring and tantalizing riddles. It wasn't a statue of gold or a weapon of war, but a simple, fired clay disc, roughly the size of a small plate. But this was no ordinary piece of pottery. Its entire surface, front and back, was covered in a dizzying array of 45 distinct, intricate symbols, all meticulously stamped into the clay in a tight, clockwise spiral before it was baked hard. This is the Phaistos Disc, and over a century after its discovery, not a single word of its message has been definitively deciphered. The immediate and overwhelming mystery of the disc lies in its manufacture. Each symbol wasn't carved or painted. It was impressed into the wet clay using a set of individual, pre-made seals or punches. Think about that for a moment. This implies the existence of a standardized set of type, a kind of movable type printing press, over 3,000 years before Johannes Gutenberg. Who created this sophisticated toolset, and for what purpose? Was the disc a unique creation, a royal decree, or was it one of many mass-produced items? The fact that nothing remotely similar has ever been found anywhere in the world only deepens the mystery. It is a complete anomaly, a solitary message in a bottle from a lost world, and we have lost the codebook. Scholars have devoted their lives to cracking this code, proposing theories that range from the brilliantly plausible to the wildly fantastical. The most persistent idea is that it represents a form of writing, but unlike the later Linear A and Linear B scripts also found on Crete, the symbols on the Phaistos disc are largely pictographic. We see recognizable figures, a man's head with a feathered headdress, a helmet, a ship, a beehive, a cat's head, and a variety of abstract marks. But are these logograms where each picture represents a whole word or concept, or are they syllabic where each sign stands for a sound like pa or tai? The spiral arrangement itself is a clue, suggesting the text was meant to be read from the outer edge toward the center, perhaps in a ritualistic or ceremonial progression. This is where the theory of it being a measuring device takes root. The precise, repeated groupings of symbols, separated by clear vertical lines, could indicate units of something. Perhaps it was a calendar measuring sacred days and agricultural seasons, with each segment marking a specific ritual or offering to be performed. The repetition of certain sequences might track lunar cycles or the movements of specific stars important to the Minoans. Another compelling, though less explored, idea is that it represents an early form of musical notation, a score for a sacred hymn or a rhythmic chant, with each symbol denoting a note, a drum beat, or a dance step, turning the disc into a conductor's sheet for a ceremony lost to time. Ultimately, the profound significance of the Phaistos disc may not be in what it says, but in what its very existence implies. It is a stark testament to a cognitive leap, a desire to encode complex, multi-layered information in a permanent, portable, and reproducible format. It challenges the very timeline of human innovation in communication technology, suggesting that the drive to compress and preserve knowledge is far older and more diverse than we ever knew. This clay disc, silent for millennia, measures not inches or hours, but the vast and frustrating distance between a brilliant ancient mind and our own desperate curiosity to understand it. From the silent, symbolic mystery of the Phaistos disc, we now move to a carving so visually striking and explicitly detailed that it seems to scream its interpretation at us across 2 millennia. Deep within the crypts of the Temple of Hathor at Denderah in Egypt, far from the sunlit courtyards visited by tourists, lies a series of stone reliefs that have become the cornerstone of one of history's most electrifying controversies. Carved during the Ptolemaic period around 100 years before the Common Era, these images are anything but the standard depictions of gods and pharaohs. They show something startlingly modern. A large glass-like bulb tapered at one end sits on a sturdy base. Encased within it is a snake, its head pointed toward one end, writhing through the air. This serpentine form is held taut by a pair of arms reaching out from the base, while a cable, unmistakably thick and braided, runs from the base of the device and connects to a small box upon which a baboon god is seated. To a modern eye, the resemblance is uncanny. It looks for all the world like a giant, ancient light bulb. Mainstream Egyptology offers a more symbolic and arguably less sensational explanation. Scholars point out that the bulb is almost certainly a representation of a lotus flower, a sacred symbol of creation and rebirth in Egyptian mythology. The snake is the familiar form of a cobra, often associated with the goddess Wadjet and divine energy. The entire scene, they argue, is a well-documented mythological vignette depicting the moment of creation itself, the emergence of the sun god from a lotus blossom that had risen from the primordial waters. The cable is interpreted as a stylized lotus stem, and the supporting arms are those of the god Heng, symbolizing infinity. This reading is consistent with thousands of other Egyptian reliefs that use complex allegory rather than literal blueprints to convey spiritual truths. Yet, the alternative theory is so compelling because it addresses a persistent, practical mystery. How did the ancient Egyptians achieve such breathtakingly precise and intricate artwork deep within the pitch-black, airless confines of tombs like those in the Valley of the Kings? The walls and ceilings are covered in millions of meticulously carved hieroglyphs and perfectly painted scenes, with no trace of soot from torches or oil lamps found in these sealed chambers. The theory proposes that the Denderah reliefs are not mythology but technical diagrams. They could illustrate a form of ancient electroplating, or, more famously, a Crookes tube or Jaissler tube, an early type of electrical discharge tube that produces a glow when a high voltage is applied across electrodes in a partial vacuum. In this interpretation, the snake represents the writhing, snaking path of a glowing electrical filament or plasma discharge. The braided cable is an insulated wire, and the box with the baboon could be a primitive battery or capacitor, with the baboon often linked to the god Thoth, the patron of knowledge, serving as a symbolic power source. If this were true, these devices wouldn't just have produced light. They might have been used to measure electrical potential or to create a specific, ritualistic glow for ceremonies dedicated to awakening the gods. The debate between these two views is a fascinating clash of paradigms. One side sees a rich, complex spiritual metaphor rendered in stone. The other sees a literal instruction manual for lost technology. Perhaps the most profound truth lies not in choosing one over the other, but in understanding how they might intertwine. For the ancient Egyptians, the line between the technological and the spiritual was likely non-existent. The energy that powered the universe was the same energy that flowed from the gods. A device that could harness and manifest that energy as a brilliant, otherworldly light would be the ultimate fusion of science and religion. It wouldn't just measure electrical current, it would measure one's proximity to the divine. The Denderah reliefs, therefore, stand as a powerful Rorschach test for the modern world. They challenge us to see beyond our own categories and consider that the greatest achievement of an ancient civilization may have been its ability to weave observation, invention, and belief into a single, luminous tapestry of understanding. Our journey into the unknown now takes a sharp turn from the grand temples of Egypt to a humble, windswept mountain in California. The year was 1961, and 3 men were prospecting for geodes near the town of Olancha. They were cracking open these round stone nodules, hoping to find beautiful crystals inside. But one of the rocks gave them something utterly inexplicable. Inside a hardened, fossil-encrusted geode was no crystal. Instead, there was a mechanical object. At its center was a cylinder of bright, machined metal. It was encircled by what appeared to be a ceramic collar, and the whole assembly was held within a hexagonal sheath of corroded copper. To anyone with even a passing knowledge of 20th century mechanics, the identification was instant and jarring. It looked exactly like a spark plug from a modern internal combustion engine. The problem was the rock that encased it. Initial geological analysis suggested the nodule had taken a very, very long time to form, potentially 500,000 years. This was the birth of the Koso Artifact, a mystery that has fiercely divided believers and skeptics for over half a century. The core of the controversy lies in that apparent age. If the object was truly 500,000 years old, its implications are staggering. It would mean that a piece of precisely machined technology existed on a North American continent where, according to all established science, the most advanced human tools were simple hand axes made of chipped stone. This single artifact would force a complete rewrite of human history, suggesting the existence of an impossibly advanced prehistoric civilization, or, in the more fringe theories, a visit from ancient astronauts who left behind a piece of their technology. The artifact was seen by some as a potential ancient energy device, a component that could measure and regulate an electrical spark, perhaps part of a larger, lost machine. It became the ultimate OOP art, an out-of-place artifact, a term for objects that seem to defy their historical context and challenge the very foundations of archaeology. Skeptics, however, were quick to offer a far more mundane and ultimately more widely accepted explanation. They argued that the object wasn't ancient at all, but a champion spark plug from the early 1920s, a common model used in Ford Model T and Model A engines. The theory goes that this spark plug was discarded on the ground, perhaps by a miner or a rancher. Over time, minerals and mud congealed around it, a process known as concretion. This isn't the slow formation of a true geode over millennia, but a relatively rapid cementing of debris that can happen in a matter of decades, especially in mineral-rich environments. The apparent age of the surrounding rock, they contend, was a misinterpretation based on the fossil shells embedded in the concretion, shells that were ancient, but that had simply been incorporated into the modern formation around the modern object. In this view, the Koso Artifact doesn't measure ancient electricity. It measures our powerful human tendency to see mystery where there is only coincidence and concretion. Yet, the mystery endures, kept alive by a few stubborn details and the artifact's own inconvenient disappearance. The original owners reportedly had it examined by a geologist who allegedly confirmed its immense age, though this report has never been made public. The object itself was last seen in the 90s and has since vanished from public view, making modern analysis with advanced techniques impossible. This absence fuels speculation, allowing both sides to hold their ground without a definitive verdict. The Koso Artifact, therefore, measures something far more profound and personal than voltage or engine timing. It serves as a perfect gauge for our own willingness to believe. It challenges us to ask where healthy skepticism ends and closed-mindedness begins, and conversely, where open-minded inquiry ends and wishful thinking begins. It stands as a permanent question mark, a rusting, hexagonal Rorschach test that asks us not about its own origin, but about ours, and about how we choose to navigate the tantalizing, often frustrating, borderland between established fact and breathtaking possibility. While the Koso Artifact remains a contentious and modern puzzle, our next discovery is a small, polished piece of rock crystal that offers a far clearer yet equally profound window into ancient ingenuity. Unearthed in 1850 by the renowned archaeologist Austin Henry Layard, it was found amidst the spectacular ruins of the ancient Assyrian palace of Nimrud, a capital of one of history's most formidable empires. The object itself is unassuming, an oval-shaped piece of naturally occurring crystal, about 1.5 inches across, painstakingly ground and polished into a slightly convex shape. It dates back to the 8th century before the Common Era. To the untrained eye, it could be mistaken for an ornate piece of jewelry or a decorative inlay. But to a physicist, its form is unmistakable. This is the Nimrod Lens, and it is one of the oldest known manufactured lenses in the world, a precision optical device that predates the formal science of optics by well over 1,000 years. The sophistication of its construction is what truly astonishes. Analysis shows it has a focal length of roughly 5 inches, meaning it could concentrate sunlight to a point, creating enough heat to ignite tinder, functioning as what we call a burning glass. More impressively, it possesses a focal point about 43 millimeters from its surface, giving it a magnifying power of around 3 times. This isn't a crude, accidental shape. It's the product of deliberate and skilled craftsmanship, a tool designed to manipulate light with a specific purpose in mind. The immediate question is, who was using it and for what incredible tasks in the heart of the brutal Assyrian war machine? One compelling theory places it in the hands of a master artisan or scribe. The Assyrians were renowned for their incredibly fine, detailed ivory carvings and for the minuscule cuneiform script that covered their clay tablets and palace walls. Holding this lens could have allowed a skilled craftsperson to execute breathtakingly intricate details, or an elderly scribe, whose eyesight was failing, to continue his vital work of recording laws, treaties, and astronomical observations. In this capacity, the lens would have been a priceless tool of precision, extending the capabilities of human vision and enabling a level of detail that would be nearly impossible with the naked eye alone. But its potential use soars even higher. The Assyrians, like many ancient cultures, were avid and sophisticated astronomers. They meticulously tracked the movements of planets and stars, believing them to be messages from the gods. Could the Nimrod lens have been part of a primitive optical instrument? If mounted in a simple frame, It could have been the key component of a rudimentary telescope, used not to see distant galaxies, but to bring the shimmering points of light in the night sky into sharper focus, allowing priests to make more precise observations of the heavens. This wouldn't have been a Galilean telescope, but a simple, powerful aid that could have given Assyrian astronomers a significant edge in measuring celestial movements and refining their complex calendars. Perhaps its most fascinating application, however, lies in a realm that feels almost mystical. The Assyrians were also advanced in medicine for their time. There are accounts of surgeries and detailed descriptions of ailments. Some scholars have proposed that a lens of this quality could have been used by a priest-physician for a very specific and startling purpose, the couching of cataracts. This ancient surgical procedure involved using a sharp needle to dislodge a clouded lens in the eye. The use of a magnifying lens would have granted the surgeon a vastly improved view of the patient's eye, turning a blind, risky procedure into something far more calculated and precise. In this light, the crystal becomes not just a tool for observation, but an instrument of healing, measuring the delicate boundary between sight and blindness. The true power of the Nimrod Lens may not be in providing a single definitive answer, but in the spectrum of possibilities it illuminates. It reveals a society that was not solely focused on conquest and domination, but one that valued precision, clarity, and the enhancement of human perception. It stands as silent, solid proof that the fundamental principles of optics, light bending through a transparent medium to enlarge or ignite, were not just theoretical concepts waiting for the Greeks or the Renaissance to discover. They were known, understood, and applied by craftsmen, astronomers, and healers in the dusty, sun-baked courtyards of Nimrud, a small crystal disc measuring not just millimeters of focal length, but the vast scope of practical scientific thought in the ancient world. This small, delicate artifact, carved from sycamore wood and discovered in an 1898 excavation of a tomb near Saqqara, Egypt, presents a puzzle that soars far above its modest size. Known simply as the Sakara Bird, it dates back to approximately 200 years before the Common Era, a time when the Ptolemies ruled Egypt. At first glance, it appears to be a stylized bird figurine, complete with a beak and eyes. But a second, closer look reveals something startlingly different. Its wings are not shaped like those of a bird in flight. They are straight, angled, and rigid, with a perfectly airfoil-shaped cross-section identical to that of a modern airplane wing. Even more telling is the tail. Instead of a bird's fanned or tapered tail, it stands upright and is squared off, resembling nothing in nature but looking exactly like the vertical stabilizer on the empennage of a modern aircraft. This is no simple toy or religious symbol. It is a carefully crafted model of something designed to fly. The implications of its design become undeniable when you put it to the test. In the late 20th century, several aerodynamics experts and hobbyists built precise, scaled-up replicas of the Saqqara Bird to see how it would perform. The results were astonishing. When launched, the model exhibits superb gliding capabilities, catching the air under its wings and sailing smoothly for considerable distances. Its airfoil shape generates lift efficiently, and that peculiar vertical tail fin provides crucial stability in flight, preventing it from spinning out of control. It performs exactly like a modern glider, a craft designed not to flap its wings but to ride on currents of air. This performance is not a happy accident. It is the direct result of a specific and sophisticated understanding of aerodynamic principles. The creator of this object didn't just carve a bird, they encoded empirical knowledge of flight into a piece of wood. So what was its purpose? If it was a measuring device, what exactly was it measuring? One compelling theory is that it was a kind of ancient wind tunnel model, a three-dimensional blueprint used by a master craftsman to teach apprentices the principles of a larger design. Perhaps it was the template for a ceremonial glider or a large kite used in religious festivals, an object meant to soar over the Nile as an offering to the sky god Horus. The Egyptians were master observers of nature, and the idea that they studied the flight of birds of prey like the falcon to distill these principles into a working model is entirely plausible. In this sense, the bird wasn't just a symbol of a deity, it was a functional representation of divine power, the power of flight itself, made tangible and understandable. Of course, the mainstream and more cautious interpretation is that it was indeed a child's toy or a ceremonial weather vane, and that its aerodynamic properties are merely an intriguing coincidence. They argue that without evidence of a propulsion system or larger manned versions, it cannot be considered proof of ancient aviation. Yet, this dismissal feels too easy, too reliant on our own preconceived notions of historical technological limits. The Sakara Bird doesn't need to be part of a fleet of pharaonic jets to be revolutionary. Its significance lies in the clear intention behind its design. It demonstrates that the fundamental physics of flight, the relationship between lift, thrust, and stability, were not only observable but were being actively applied and tested long before we ever credited humanity with such insight. This unassuming wooden model, therefore, measures something far more abstract than distance or time. It measures the altitude of human curiosity. It stands as a silent testament to a mind that looked at a bird circling in the thermal currents above the desert and wondered not just how, but if that principle could be captured and replicated. It challenges the linear narrative of invention, suggesting that the spark of discovery can flash into existence, be beautifully realized in a single, perfect object, and then lie dormant for centuries, waiting for another era to look back and finally understand what it was they were truly trying to achieve. Leaving behind the silent, aerodynamic mystery of the Sakara Bird, we now plunge into the chaotic, fiery waters of medieval warfare, to a weapon so potent and so terrifyingly advanced that its very essence remains one of history's most fiercely guarded secrets. This is not a single, static artifact you can hold in a museum. It is a concept, a formula, a system of destruction that became the ultimate strategic deterrent of its age, Greek fire. First unleashed by the Byzantine Empire in the 7th century during a desperate siege of Constantinople, this was no ordinary incendiary. It was a liquid fury that defied all contemporary understanding of combat. It clung to the surfaces of wooden ships like a malevolent, living entity. It roared and hissed as it burned, even on the surface of the sea itself, and legend claims that water only fed its rage, making attempts to douse it utterly futile. For the enemies of Byzantium, often the formidable Arab fleets, encountering it was like facing a dragon unleashed by human hands, a nightmare from which there was no waking escape. The true brilliance of Greek fire, and why it fits so perfectly among these complex devices, was not just in its mysterious chemical composition, but in its sophisticated delivery system. This was not hurled in pots from catapults. It was a precisely engineered weapon of measured application. The key to its deployment was a complex device known as a siphon, a pressurized brass pump mounted on the decks of Byzantine dromon warships. Operators trained in this sacred art would pump the preheated, viscous liquid from a sealed, insulated tank through a large tube. At the end of this tube was a nozzle, often crafted in the shape of a grotesque animal or dragon's head. When a valve was opened and a lit torch applied, the mixture would erupt from the nozzle not as a simple stream, but as a roaring, continuous jet of flame that could be accurately projected over dozens of meters, engulfing enemy vessels in an inescapable inferno. This entire apparatus, the pressurized tank, the pump, the valve, and the nozzle, formed a single, terrifying device designed for one purpose: to measure and project controlled chemical combustion with devastating accuracy on the unpredictable canvas of the open sea. Unraveling the recipe for this ancient napalm has consumed historians and chemists for centuries. The secret was so closely guarded that it was known only to a select few, perhaps even only one family at a time, and it died with the fall of Constantinople in the 15th century. Contemporary descriptions provide tantalizing clues. It was reportedly a thick, sticky liquid like pine sap, and was preheated in the ship's tank before battle to make it flow more easily. The most credible theories point to a base of crude petroleum or naphtha, drawn from natural oil seeps around the Black Sea, mixed with raw pine resin for adhesion and possibly quicklime, a substance that generates immense heat when it contacts water, explaining its infamous aqua ignition. Other proposed ingredients include sulfur for a fiercer burn or saltpeter to introduce an early form of oxidization, a primitive step toward the chemistry of gunpowder. The exact proportions and any potential catalytic agents, however, are lost. The Byzantines weren't just mixing a potion, they were orchestrating a complex exothermic reaction, understanding the properties of each component on a level that would not be seen again in warfare for hundreds of years. The strategic impact of this technological marvel cannot be overstated. For centuries, it was the cornerstone of Byzantine naval doctrine, the equivalent of a nuclear deterrent in the medieval world. The mere threat of its use was often enough to scatter invading fleets or force unfavorable terms in negotiation. It secured the maritime borders of the empire, protected its capital, and preserved Roman culture in the East against overwhelming odds. Its existence speaks to a society that, even in what we often dismiss as the Dark Ages, maintained a vibrant thread of advanced scientific and engineering thought. The chemists in the imperial workshops were the anonymous geniuses of their day, and their pressurized siphons were masterpieces of mechanical engineering, requiring precise machining of metals and an understanding of pressure and flow dynamics that was utterly unparalleled. Greek fire, therefore, measured far more than the combustion rate of a mysterious compound. It measured the terrifying gap in technological capability between Byzantium and its rivals, the psychological impact of overwhelming and inexplicable force, and the incredible lengths to which human ingenuity will go when driven by the primal need to survive. It stands as a blazing testament to the fact that some of history's most profound scientific advances were born not in peaceful laboratories, but in the forge of war, their secrets as fiercely protected as any holy relic. From the blazing, volatile science of Greek fire, we travel to a monument of serene and silent endurance, a testament to a completely different kind of ancient mastery. In the heart of modern Delhi, within the complex of the Qutb Minar, stands a solitary sentinel that has defied not just invaders but time itself. This is the Iron Pillar of Delhi, a 23-foot-tall column of wrought iron weighing over 6 tons. Its origin story is inscribed upon it in Sanskrit, telling us it was erected as a standard in honor of the Hindu god Vishnu during the reign of King Chandragupta II around the year 400 of the Common Era. For over 1,600 years, it has been exposed to the sweltering heat of the Indian sun, the drenching torrents of the monsoon season, and the pollution of a modern megacity. And yet, against every law of chemistry we understand, it shows almost no sign of rust. This isn't a passive relic, it is an active, breathing demonstration of a metallurgical genius so profound that it continues to stump scientists today. The mystery of its preservation is not magic, but a breathtakingly sophisticated accident of chemistry and craftsmanship. Modern analysis using techniques like X-ray diffraction has revealed the pillar's secret. It is made from a surprisingly pure form of wrought iron, but its true genius lies in its unique protective coating. Unlike modern stainless steel, which uses chromium to resist corrosion, the Delhi pillar protects itself. Its surface has developed a thin, continuous, and remarkably stable film of a compound called mesawite. This protective layer is just 50 to 600 micrometers thick, about the width of a human hair, but it is incredibly effective, forming a perfect barrier that prevents oxygen and moisture from reaching the underlying metal and triggering the destructive process of rust. The formation of this film was no accident. It is the direct result of the pillar's specific chemical composition, which includes a high percentage of phosphorus and a surprisingly low amount of sulfur and manganese. Ancient Indian smiths, working with large forge-welded masses of iron, used a particular method that infused the metal with phosphorus from the ore and charcoal fuel. This was a delicate balance. Too much phosphorus can make iron brittle, but the right amount, combined with the hammering and working of the metal, created a perfect recipe for long-term survival. It is a passive protective layer that has been self-healing and self-renewing for 16 centuries, a feat of material science that modern engineers have only recently begun to fully appreciate and replicate. But to see the iron pillar as merely a rust-resistant monument is to miss half of its story. The inscription itself, a eulogy to a great king, hints at a deeper purpose. It states that the pillar commands the earth and that the king's fame was crossing the 7 mouths of the river Sindh, or the Indus. This cosmic language suggests the pillar was more than a simple flagpole. Many scholars believe it was originally an astronomical instrument, a giant gnomon at the center of a vast sundial, erected in the ancient city of Udayagiri, a site filled with astronomical and cosmological significance. Its perfectly cast and aligned form would have cast a sweeping, precise shadow across calibrated markers on the ground. This would have allowed priests and astronomers to accurately measure the passage of the hours and track the changing positions of the sun throughout the year, marking solstices, equinoxes, and the vital seasons for agriculture and religious ceremony. In this role, the pillar wasn't just a symbol of a king's temporal power. It was a device that measured the very movement of the cosmos, linking his reign to the eternal, unchanging cycles of the heavens. The pillar's potential celestial connections run even deeper. Some researchers have proposed that its original location and orientation were carefully chosen to align with specific stars or constellations important in Vedic astrology, acting as a fixed reference point in a complex landscape of temples and caves designed for astronomical observation. It may have served as a permanent, indestructible meridian marker, a foundational piece of an ancient observatory. This transforms the pillar from a static object into a dynamic component of a larger scientific apparatus. Its incredible durability was not just a happy byproduct of good metalworking. It was an essential feature, an astronomical instrument meant to last for generations, to provide consistent, reliable data century after century, required a material that would not warp, crack, or corrode. The iron pillar of Delhi is therefore a perfect fusion of form and function. Its physical composition was engineered to ensure its purpose as a measuring device would be eternal. The ultimate wonder of the iron pillar is the stark contrast it presents to the narrative of linear technological progress. This level of empirical metallurgical knowledge appears in the historical record, achieves a near-perfect result, and then seems to vanish. Later Indian ironworking, while skilled, did not consistently produce objects with this same legendary resistance. The specific, localized knowledge of the Udayagiri ironsmiths, the precise mix of ore, the particular forging techniques, the understanding of how phosphorus content affected long-term stability, appears to have been a peak that was later forgotten or could not be replicated on a wider scale. It stands as a powerful reminder that technological advancement is not a smooth, ever-upward climb, but a landscape of isolated peaks and hidden valleys of lost wisdom. The pillar does not boast, it simply stands. It measures not just the passage of shadows or the composition of alloys, but the fleeting nature of human knowledge itself, proving that a civilization can touch a height of understanding so sublime that it takes the world over a millennium to even begin to comprehend how they did it. If Greek fire was a weapon of terrifying public spectacle and the iron pillar a monument of silent public endurance, then our next artifact is the exact opposite, a deeply private, utterly impenetrable secret. This is the Voynich Manuscript, a book that seems to actively defy understanding. Imagine a 240-page codex, beautifully illustrated on fine vellum, its pages filled with looping, elegant handwriting in an alphabet that has never been seen anywhere else on Earth. It is populated by a surreal dreamscape of impossible plants, flora, with roots like animal claws and leaves that seem to pulse with an alien life force. There are intricate diagrams of celestial spheres populated by suns and moons with human faces, and perhaps most bizarrely, page after page of plump, naked women bathing in a complex, interconnected system of green, flowing pipes and pools. Carbon dated to the early 15th century in northern Italy, this book is a perfect storm of mystery. It has a known origin in time and place, a physical form we can hold, and a visual language that is both richly detailed and completely, utterly indecipherable. It is a locked door for which no key has ever been found. Theories about its purpose are as numerous and varied as the strange plants in its herbal section, and each one proposes a different form of measurement. The most persistent idea is that it is a pharmacopoeia, a detailed manual of herbal medicine. The countless illustrations of unrecognizable plants could be encodings of real botanical knowledge, with their bizarre features acting as a visual shorthand for their properties or preparation. The text, in this view, would be the dosage instructions, the methods of concoction, and the ailments each mixture was meant to treat. It would be a device for measuring and administering the healing power of nature, its code protecting valuable trade secrets or the sacred knowledge of a particular guild of healers from prying eyes. Another compelling school of thought points to the astrological and cosmological sections, the intricate fold-out pages showing concentric circles of stars, suns, and zodiac symbols suggest a deep engagement with the heavens. Perhaps the manuscript is an elaborate astronomical almanac or a device for calculating and measuring celestial cycles. The strange, biological sections with the bathing nymphs could be a metaphorical representation of the body's humors or the flow of spiritual energy, linking macrocosm to microcosm in a way typical of Renaissance esoteric thought. In this interpretation, the book doesn't just describe the universe, it provides a framework for measuring one's place within its spiritual and physical architecture. Then there is the possibility that it is a masterwork of early cryptography. Some of the most brilliant codebreakers of the 20th century, including teams from the First and Second World Wars, have turned their skills to the Voynich and failed completely. The text displays statistical patterns found in natural language, but it doesn't match any known tongue. This has led to theories that it could be a very sophisticated cipher, perhaps even a synthetic language created to record a new form of philosophy or science that was too radical for its time. If so, the book itself is the ultimate measuring device for human ingenuity, a puzzle box designed to test the limits of intellectual decryption across centuries. And of course, there is the theory that it is all an elaborate, brilliant hoax, a Renaissance-era forgery designed to separate a wealthy, gullible patron from his gold. Proponents of this idea point to the repetitive, meaningless nature of the text's patterns and the fantastical, impossible nature of the illustrations. Yet, even if it is a hoax, the question remains: why go to such excruciating, expensive, and time-consuming lengths? The quality of the vellum, the complexity of the illustrations, and the sheer consistency of the unknown script across hundreds of pages represent an investment of years. A hoax of this magnitude would itself be a technological marvel, a device for measuring not herbs or stars, but human credulity and the immense value placed on the appearance of secret knowledge. The enduring power of the Voynich Manuscript lies in its resistance to any single, comfortable explanation. It exists at the razor's edge between profound genius and sublime nonsense. It challenges our very need to categorize and understand. Every statistical analysis of its text, every botanical comparison of its plants, every historical attempt to place it within a known tradition of writing, ultimately leads to a dead end. It is a perfect artifact of the unknown. It doesn't measure physical properties. It measures the boundaries of our own knowledge and the profound human desire to find meaning, even in the most beautifully constructed void. It is a mirror reflecting not a solution, but our own relentless, frustrated, and utterly fascinated curiosity back at us. Stepping away from the cryptic pages of the Voynich Manuscript, we journey to a time and place where measurement was not about hidden knowledge, but about saving lives on a massive scale. In the year 138 of the Common Era, the court of the Han Dynasty in China was shaken quite literally by news of a devastating earthquake in a western province hundreds of miles from the capital. But the court officials were not taken by surprise. They had been warned hours before any messenger could have possibly arrived. Their early alert came not from a runner on a horse, but from a magnificent and mysterious bronze instrument that stood in the palace, the seismoscope of Zhang Heng. This was no simple urn. It was a masterpiece of mechanical intuition, a device that could feel the faintest shudder of the earth and point a claw in its direction, achieving a feat of detection that would not be replicated in the West for over 1,500 years. The apparatus itself was a work of both art and science. Imagine a large bronze vessel, perhaps 6 feet in diameter, adorned with 8 dragons snaking down its sides, each one facing a primary direction of the compass. Curled beneath each dragon's fearsome head sat a bronze toad, its mouth wide open in anticipation. The outside was ceremonial and imposing, but the true genius was hidden within. Historical accounts describe a complex internal mechanism centered around a heavy inverted pendulum, a mass suspended freely in the center of the vessel. This pendulum was delicately connected to a series of levers and arms that led to the mouths of the dragons. The entire system was precisely calibrated so that the slightest vibration from a distant earthquake would cause the central pendulum to swing. This motion would trigger just one of the many levers, which would in turn release a heavy bronze ball held clutched inside a dragon's mouth. The ball would drop with a loud, clanging report directly into the waiting mouth of the toad below, clearly announcing not only that an earthquake had occurred, but from which cardinal direction the seismic waves had originated. The sophistication of this design reveals a breathtakingly modern understanding of wave propagation. Zhang Heng's device didn't just detect shaking. It discerned the direction of the initial seismic wave, known today as the P wave, which is the first and fastest energy to radiate from an earthquake's epicenter. By isolating this initial jolt and using it to activate only one mechanism aligned against its direction of travel, the seismoscope effectively filtered out the local, chaotic rumbling that would follow, pinpointing the source with astonishing accuracy. This principle of directional sensing is fundamental to modern seismology, yet it was mechanically encoded in bronze nearly 2 millennia before the science was formally established. It was a machine that measured the invisible, translating the Earth's deep, subterranean groans into a clear, unambiguous signal that could be seen and heard by everyone in the court. Beyond its mechanical wonder, the seismoscope served a profound and practical purpose for the Han bureaucracy. In a vast empire where communication could take weeks, an early warning of a distant earthquake was invaluable. It allowed the imperial court to quickly mobilize relief efforts, send officials to assess damage, and preemptively dispatch troops to maintain order in regions suddenly thrown into chaos. It transformed disaster response from a reactive scramble into a measured, proactive strategy, but its function was also deeply cosmological. To the Han Chinese, earthquakes were not random acts of nature. They were seen as ominous signs from heaven, potential indications of imperial misrule or cosmic imbalance. A device that could objectively measure and verify these events stripped them of some of their superstitious terror. It brought them into the realm of the observable and the manageable, reflecting a sophisticated empirical philosophy that sought to understand the natural world through careful observation and ingenious instrumentation. Zhang Heng's seismoscope, therefore, measured more than just tectonic shifts. It measured the Han dynasty's monumental confidence in human reason to decipher the universe's most violent secrets, a bronze sentinel standing guard between an empire and the unpredictable earth beneath its feet. From the sophisticated seismic sentinel of ancient China, we now travel thousands of miles and more than 1,000 years further back in time, to a discovery that fundamentally rewrote our understanding of prehistoric Europe. It was 1999, and 2 treasure hunters were illegally using a metal detector on a wooded hilltop in Nebra, Germany. What they unearthed would eventually be recognized as one of the most significant archaeological finds of the 20th century, though they initially saw it only as a bizarre piece of scrap metal destined for the black market. After a dramatic sting operation, the object was recovered by authorities and authenticated, a nearly flawless bronze disc about 12 inches in diameter, inlaid with stunning gold symbols. But its true shock was its age. Scientific analysis placed its creation at around 1,600 years before the Common Era, in the early Bronze Age. This was the Nebra Sky Disc, and it instantly became the oldest known concrete depiction of the cosmos anywhere in the world. A sophisticated astronomical device crafted over a millennium before the Iliad was composed and 3,600 years before Galileo turned his telescope to the heavens. The imagery on the disc is both beautiful and explicitly celestial. A central cluster of 7 gold dots has been almost universally identified as the Pleiades star cluster, a key marker in ancient calendars across many cultures. A large golden circle and a crescent moon, which was originally attached and could be moved, complete the main tableau, but the disc didn't stop there. Later additions by its creators show 2 golden arcs along the rim, representing the horizon, and a final, mysterious third arc at the bottom that has been interpreted as a solar bark, a mythological vessel believed to carry the sun across the sky or through the underworld at night. This was not a random arrangement of pretty shapes. It was a complex, layered codex of astronomical knowledge rendered in precious metal. Its primary function was almost certainly as a sophisticated calendrical computer, a device to measure and harmonize the often conflicting cycles of the sun and the moon. The lunar calendar, based on the moon's 29.5-day cycle, is about 11 days shorter than the solar year. This discrepancy causes lunar months to drift through the seasons over time. Ancient agricultural societies needed a way to keep their lunar-based rituals and months in sync with the solar-based seasons for planting and harvest. The Nebra Sky Disc provided a brilliant mechanical solution. The specific placement of the Pleiades cluster relative to the Sun and Moon would have been a critical visual signal. In the central German sky of the Bronze Age, the Pleiades disappeared behind the Sun in spring and reappeared in the autumn. By observing the position of the crescent moon next to the Pleiades at specific times, users could determine when it was necessary to intercalate or add an extra lunar month to bring the two calendars back into alignment. This was a monumental intellectual achievement, a way of literally holding time in your hands and ensuring the harmony of the celestial and terrestrial worlds. This portable observatory also hints at a profound, unified worldview that blended science, religion, and power. The hilltop where it was found, Mittelberg, was itself a carefully chosen observatory with the Brocken Mountain, the highest peak in northern Germany, serving as a natural marker for the sunset on the summer solstice. The disk was likely used by a powerful, elite class of priest astronomers who could read the sky. Their ability to predict the solstices, to announce the correct time for sowing and reaping, and to perform rituals that ensured the sun's continued journey on its bark would have granted them immense authority. They weren't just stargazers, they were the intermediaries between their people and the cosmos, and the disk was their ultimate tool, a physical manifestation of their sacred knowledge. It transformed the vast, intimidating expanse of the night sky into a manageable, measured system, reinforcing social order and spiritual belief through precise astronomical observation. The existence of the Nebra Sky Disc is a powerful corrective to a long-held historical bias that viewed prehistoric Central Europe as a cultural backwater, a land of barbarians waiting for civilization to arrive from the Mediterranean and Near East. This disc proves the opposite. It reveals a society with a complex cosmological understanding, advanced metallurgical skills capable of intricate gold inlay on bronze, and a structured, hierarchical social system that could support and value such specialized knowledge. It is a testament to a shared pan-European urge to understand the universe, one that emerged independently and with stunning sophistication. The disk doesn't just measure the solstice or the lunar month. It measures the impressive intellectual height reached by Bronze Age minds, forcing us to look at a familiar night sky and see it through the eyes of a brilliant, ancient culture that mapped it all out in gold and bronze 3,600 years ago. Moving from the celestial gold of the Nebra Sky Disc, we encounter an object that is the very embodiment of a hands-on, tangible mystery. Scattered across the vast expanse of the former Roman Empire, from the wet, misty fields of Britain to the sun-baked ruins of Hungary, are hundreds of small, hollow, bronze artifacts that have stubbornly resisted explanation for centuries. Each one is a geometric marvel, a dodecahedron, a 12-sided solid, with each pentagonal face featuring a circular hole of varying diameter. Protruding from each of its 20 corners is a small, solid knob. Ranging in size from a golf ball to a large apple, these objects date from the 2nd and 3rd centuries of the Common Era. They are exquisitely crafted, showing signs of skilled metalworking, yet not a single shred of written record, no inscription, no fresco, and no historical text from the Romans themselves mentions what they are or what they were for. The Roman Dodecahedron is a perfect, silent puzzle left on our doorstep by one of history's most meticulous record-keeping civilizations. The sheer number of theories proposed for its function is a testament to both its intriguing design and our own desperate curiosity. One of the most persistent ideas casts it as a sophisticated surveying and distance measuring tool. The theory suggests that by sighting through the different-sized holes against a known landmark or a calibrated staff, a user could calculate distances, perhaps for military range finding or for civil engineering projects like road construction. The knobs would provide a secure grip for aiming and rotating the device. This would make it a kind of analog computer, a portable device for measuring the landscape with geometric precision, a tool perfectly suited for the empire builders who famously marched in straight lines across continents. Other theories delve into the domestic and practical. Some have proposed it was a knitting tool for creating gloves, with the knobs used to form and hold the fingers of woolen mittens. Another suggestion is that it was a decorative candle holder with wax dripping artistically through the holes, though the lack of wax residue on recovered specimens makes this unlikely. There are more whimsical ideas, like a dice for a complex betting game or a children's toy, but the consistent high quality of the bronze and the clear absence of wear and tear from heavy handling argue against mere amusement. Perhaps the most captivating theories connect the dodecahedron to the realm of the spiritual and the celestial. The geometry itself is deeply symbolic. The 12 faces could represent the 12 signs of the zodiac, and the device could have been used as an astronomical calculator to determine the optimal dates for planting crops based on the angle of the sun. It might have been a ritual object used by priests for divination, a sacred device for measuring the favor of the gods. Its frequent discovery in coin hoards and burial sites with other valuables suggests it was considered a prized possession, an object of significant personal or communal value, not just a common tool. The most compelling aspect of the dodecahedron is what its very existence says about Roman society. Here was an empire capable of mass-producing such a complex, mathematically precise object and distributing it across thousands of miles. This implies a shared knowledge, a common understanding of its purpose among the people who made and used them, an understanding that was so commonplace it never needed to be written down. Its mystery is born from a catastrophic cultural amnesia following the empire's collapse. The knowledge wasn't lost because it was secret, it was lost because it was ordinary. The Roman dodecahedron, therefore, measures something far more poignant than distance or light. It measures the fragile nature of common knowledge itself, serving as a stark bronze reminder that the most mundane objects of a culture can become its most impenetrable mysteries once the living thread of understanding is severed. It stands not as a failure of Roman engineering, but as a silent monument to everything that can be forgotten. While the Romans were distributing their enigmatic bronze dodecahedrons across Europe, a world away in South India, an entire civilization was building a calendar system of such breathtaking complexity and accuracy that it wove the fabric of the cosmos directly into the rhythm of daily life. This was the time of the Tamil Sangam, a golden age of literature and learning that flourished from as early as 300 years before the Common Era. The Sangam poets did more than just compose beautiful verses. They encoded a sophisticated scientific worldview, one that understood the movements of the heavens not as abstract theory, but as a practical guide for survival and prosperity. Theirs was a world measured not with bronze gadgets, but with shadows, water, and the meticulous observation of the natural world, creating a timekeeping legacy that stands as a monumental achievement of the ancient world. The foundation of this system was a deep, empirical understanding of celestial mechanics. Ancient Tamil astronomers had precisely calculated the duration of the solar year, the lunar month, and the intricate dance between the two. Their calendar was not a simple list of days. It was a complex, interlocking system that divided the year into 6 precise seasons, each exactly 60 days long, based on the sun's apparent movement. These seasons, from the early downpours of the monsoon to the intense period of harvest, were not arbitrary. They were defined by specific asterisms, the Sun's position relative to 27 different star constellations, and the subtle changes in wind patterns, temperature, and ocean currents. This was ecology and astronomy fused into a single, seamless science. For a civilization deeply dependent on agriculture and maritime trade, this was not academic. It was essential. Knowing the exact window to sow seeds or to set sail on the predictable monsoon winds was the difference between abundance and famine, between a successful trading voyage and a ship lost at sea. To track these celestial cycles on the ground, the Tamils engineered elegant and precise instruments. One of the most widespread was the Najagai shadow clock. This was a simple yet brilliant device, a calibrated rod placed in the center of a hemispherical bowl. As the sun traveled across the sky, the rod's shadow would move along the inscribed lines inside the bowl, dividing the daylight hours into units as precise as 24 minutes. This wasn't just for knowing the time of day. It was a tool for celestial navigation and for timing religious and social rituals to the exact moment deemed most auspicious by the planetary positions. For more granular timekeeping, especially at night or on overcast days, they used water clocks known as Najagai Kundam. These were not just jars with a hole in the bottom. They were carefully calibrated vessels where the steady drip of water through a small aperture would measure the passage of time against marked levels, allowing for the division of the day into consistent, measurable units regardless of the weather. Perhaps their most astonishing application of this knowledge was in the realm of oceanography. The Sangam literature contains remarkably accurate descriptions of tidal patterns, correlating the ebb and flow of the sea with the phases of the moon long before this connection was widely established in the West. They understood the spring and neap tides, the variation in tidal heights, and used this knowledge to guide their extensive maritime trade with the Roman Empire and Southeast Asia. A ship's captain consulting a Sangam-era calendar would know not just the day he should depart, but the precise Najagai, the exact unit of time, when the tides would be most favorable for leaving the safety of the harbor. This transforms their calendar from a simple almanac into a dynamic, multifaceted instrument for measuring and predicting the behavior of the natural world on a truly grand scale. The enduring legacy of the Sangam calendar system is a powerful testament to a different kind of scientific tradition, one that was deeply holistic and preserved through an unbroken chain of oral and written tradition. Its accuracy rivaled, and in some cases surpassed, the calendrical methods of medieval Europe, yet it remains a footnote in most mainstream narratives of scientific history. This omission speaks less to its sophistication and more to the biases of how history is often written. The Tamil achievement was not a single, mysterious artifact waiting to be dug up, but a living, breathing system of knowledge integrated into poetry, agriculture, and navigation. It measured more than just solar cycles or tidal hours. It measured the intellectual height of a civilization that saw no divide between the stars above and the soil below, viewing the entire universe as a single, magnificent clockwork to be observed, understood, and harmoniously lived within. Long before the magnetic compass guided European explorers across oceans, a civilization flourishing in the humid lowlands of what is now Mexico was already holding the secret of magnetism in their hands. The Olmecs, often called the mother culture of Mesoamerica, are renowned for their colossal stone heads and their foundational influence on later societies like the Maya and Aztec. But beyond their monumental art, they left behind a collection of small, enigmatic artifacts that hint at a far more sophisticated understanding of the natural world. Among their most intriguing relics are carefully worked bars and discs made of a peculiar, heavy black mineral, magnetite. This naturally magnetic lodestone, when suspended or placed on a float in water, will consistently align itself along a north-south axis. The staggering implication is that the Olmecs, as early as 1500 years before the Common Era, may have possessed and utilized a functional compass. The evidence for this is both physical and compelling. Archaeologists have unearthed several of these magnetite objects at key Olmec sites like San Lorenzo. They are not raw, unworked stones. They have been meticulously polished and shaped into consistent geometric forms, most notably concave bars and discs. This deliberate craftsmanship is crucial. A raw, irregular lump of lodestone might spin erratically, but a carefully balanced, symmetrically shaped bar would rotate smoothly and settle into a reliable orientation. The concave shape of some bars is particularly telling, as it could have served as a perfect cradle to hold a floating needle or to be suspended itself on a string with minimal friction. These weren't trinkets or random pieces of ore. They were precision-engineered tools designed to exploit a specific physical property. So what purpose did this ancient guidance system serve? The most practical theory points to urban planning and celestial alignment. The Olmecs were master builders, constructing elaborate ceremonial centers with large earthen pyramids and vast plazas. Aligning these structures with precise cardinal directions was of immense cosmological importance, connecting the earthly realm with the heavens. Using a lodestone compass would have provided a far more accurate and reliable method for establishing true north than simply observing the sun or stars, especially under the often cloudy Mesoamerican skies. This could explain the remarkable precision found in the orientation of their cities. Perhaps the most evocative image is that of an Olmec architect priest using a floating magnetite disc to lay out the precise axis for a new temple, ensuring it was in perfect harmony with the invisible forces of the earth itself. This practical application likely bled directly into the spiritual. For the Olmecs, the world was alive with sacred energy and powerful forces. The ability of a stone to move on its own, to point unerringly in one direction without any visible cause, would have been seen as profound magic. The lodestone didn't just point north, it was a physical manifestation of a cosmic order, a direct line to the will of the gods or the breath of the earth. It could have been used in divination rituals to determine auspicious dates, or to align burials and offerings with the spiritual currents of the universe. In this sense, the compass was a dual-purpose device, a practical tool for the builder and a sacred instrument for the priest, measuring both geographical direction and spiritual alignment. The existence of the Olmec compass forces a dramatic rethinking of the history of technology. For centuries, the invention of the magnetic compass was credited to the Chinese during the Han Dynasty, around the 2nd century before the Common Era, with its first clear use for navigation documented later. The Olmec artifacts predate this by nearly a millennium. This doesn't necessarily mean the Olmecs invented it first, and the idea traveled across the Pacific, an unlikely prospect. Instead, it points to a powerful phenomenon, the independent discovery of natural principles by completely isolated cultures. Both civilizations encountered lodestone, observed its unique properties, and through brilliant empirical experimentation, found a way to harness it. The Olmec compass stands not as a challenge to Chinese ingenuity, but as a testament to the universal curiosity of the human mind, proving that the spark of discovery can ignite in multiple places at once, fueled by the same desire to measure, navigate, and understand the mysterious world we all inhabit. While the Olmecs may have used lodestone to align their world with the cosmos, the Inca Empire of South America developed a system for recording that world that was so revolutionary. It defies our very definition of writing. Imagine an empire stretching over 2,500 miles of rugged Andes mountains, governing over 10 million people across hundreds of distinct cultures and languages, all without a single piece of paper, a single clay tablet, or a single system of alphabetic script. This was the reality of the Inca, and their ability to manage this vast, complex state rested on a technology of stunning elegance and sophistication, the Quipu. Far more than simple accounting tools, these intricate arrays of knotted strings were a vibrant, dynamic recording system, a three-dimensional library of an entire civilization's knowledge, and perhaps one of the most misunderstood measuring devices in human history. At its most fundamental level, a quipu is a collection of cords, often made from cotton or the hair of llamas or alpacas. A primary cord serves as the backbone from which dozens, sometimes hundreds, of pendant cords are suspended. But this is where the simplicity ends. Each element of a quipu is a variable in a complex code. The position of a knot on its cord represents a numerical value using a base 10 decimal system, with different knot types denoting units, tens, hundreds, and so on. The color of the cord itself is not decorative, it is semantic. A red cord might represent the Inca army, yellow could signify gold, while green might denote a harvest of maize. The material, the spin direction of the fibers, the way cords are attached to each other, even the spatial relationship between knots, every detail was a potential carrier of information. This allowed Quipucamayocs, the highly trained record keepers, to log immense datasets, census figures, tribute inventories, astronomical cycles for the agricultural calendar, and military organization with a precision that would rival any modern spreadsheet. However, the true revolutionary mystery of the quipu lies beyond mere arithmetic. Spanish chroniclers from the 16th century reported with astonishment that the Inca used these knotted strings to record not just numbers, but history, laws, and epic poetry. They claimed that when a runner arrived at an administrative center, the Quipucamayok would listen to the message and then tie a new series of knots, effectively writing down the narrative. Later, another specialist could read the quipu back, recounting the entire story verbatim. This suggests the quipu was not a text in the Western sense, but a sophisticated mnemonic device, a tactile, physical trigger for a trained memory. The knots and colors did not encode the words themselves, but the key themes, events, and structures of a narrative that was then performed from a memorized oral tradition. It was a symbiotic system where the physical artifact and the trained human mind worked in perfect concert to store and retrieve vast amounts of non-numerical information. This challenges a deeply ingrained Eurocentric bias that equates literacy solely with the representation of speech sounds on a flat surface. The Inca developed a system of recording information in 3 dimensions, using texture, spatiality, and chromatic symbolism. It was a form of literacy, but one that operated on a completely different sensory and cognitive plane. Recent anthropological work has uncovered something even more astounding. In a remote Andean village, researchers found a community still using quipus in the 20th century, not for Inca census data, but to document local community histories and the intricate rituals of animal husbandry. Even more fascinating, the knots were used to record complex conflict mediation cases, with different knot types representing the parties involved, the nature of the dispute, and the resolution reached. This transforms the quipu from a simple ledger into a legal document, a repository of social contracts and justice. The tragic end of the quipu's story adds a layer of profound loss to its mystery. Recognizing the quipu as a potent symbol of indigenous authority and a competing system of knowledge, Spanish colonizers and Catholic priests systematically sought out and destroyed them by the thousands in the 16th century, viewing them as idolatrous objects or tools of pagan rule. This was an intellectual genocide, the burning of a people's library. Today, only about 600 quipus are known to survive in museums and collections around the world, and the full cipher for their non-numerical codes died with the last great Quipucamayos. The surviving quipus are now silent, their stories locked away within their intricate knots. They stand as a hauntingly beautiful monument to a different way of thinking, a different way of measuring and remembering the world, not in ink but in fiber, not in letters but in loops and hitches, a testament to the fact that the human impulse to record our existence can take forms far more diverse and ingenious than we have ever imagined. Imagine a grand imperial procession during the Jin dynasty, a spectacle of power and precision winding its way through mist-shrouded valleys. At the head of this magnificent convoy, surrounded by soldiers and officials, rolls a chariot unlike any other. Perched atop it is not a warrior, but a carved wooden figure, its arm outstretched. As the procession turns a corner, then another, twisting and doubling back through the complex terrain, the figure does not follow the path. Its arm remains stubbornly, miraculously fixed, pointing unerringly toward the south. This was no mystical totem. It was a masterpiece of mechanical engineering known as the South-Pointing Chariot, a non-magnetic compass built over 17 centuries ago that stands as one of history's most brilliant and counterintuitive inventions. The sheer genius of this device lies in its defiance of expectation. In a world where we instinctively link direction finding to magnetism, the South-Pointing Chariot achieved its unwavering guidance through pure, unadulterated mechanics. It was a computer made of wood and gears, an analog marvel that calculated direction through movement. The core of its operation was a fiendishly clever differential gear system, a concept so advanced it wouldn't be widely used in the West until the invention of the modern automobile. Here's how it worked. The chariot's two massive wheels served as the input sensors. As the chariot moved in a straight line, both wheels turned at the same rate, and the central gears remained balanced, keeping the pointer statue locked in position. But when the chariot turned, the wheels would rotate at different speeds, the outer wheel covering more ground than the inner one. This difference in rotation was captured by the gears. The differential mechanism would then translate that difference into a compensating rotation of the statue on its platform, but in the exact opposite direction of the turn. If the chariot turned 90 degrees to the east, the gears would command the statue to rotate 90 degrees to the west, perfectly cancelling out the movement and ensuring the arm never wavered from its southern bearing. It was a closed-loop feedback system, a mechanical brain that constantly measured the chariot's own movements to correct for any error, maintaining a fixed celestial reference with stunning accuracy. This was not a device for precise navigation across trackless oceans or deserts. Its purpose was far more specific and symbolic. Historical records suggest it was used primarily in imperial processions, a moving testament to the emperor's divine mandate to maintain order and direction for the entire realm. In a military context, it could have been invaluable for commanding officers leading large, cumbersome formations through featureless or confusing landscapes, providing a constant, reliable reference point to maintain overall orientation and coordinate troop movements without relying on the sun or stars, which could be obscured by weather or smoke. It measured more than just cardinal direction. It measured the technological and intellectual supremacy of the Chinese state, a rolling advertisement of their unparalleled engineering prowess that would have left foreign ambassadors and rival chieftains in awe. The philosophical implications of the chariot are as profound as its mechanical ones. For the ancient Chinese, the concept of a fixed center, an unchanging point of reference around which chaos could be organized, was a core tenet of cosmology and statecraft. The south-pointing chariot was the physical embodiment of this principle, It demonstrated that constancy could be engineered, that chaos could be measured and counteracted through human ingenuity. It wasn't magic, it was math made manifest in lacquered wood and bronze gears. This machine stands as a monumental rebuttal to the notion that complex automation was a European invention of the industrial age. The Chinese engineers of the 3rd century were not just tinkerers, they were roboticists in spirit, creating a machine that could sense its environment, process that information mechanically, and execute a corrective action without any human intervention beyond the initial push. The south-pointing chariot, therefore, does more than just point south. It points us toward a completely different understanding of technological history, one where the path to automation was being paved on the Silk Roads of ancient China long before the first clockwork knights of Europe ever stirred. Leaving behind the intricate mechanical genius of the Chinese south-pointing chariot, we now set sail into the frigid, fog-shrouded waters of the North Atlantic, where Viking navigators faced a challenge that would stump modern sailors even with today's technology. How do you maintain a straight course across a trackless ocean for weeks on end when the sky is a perpetual, featureless gray dome, hiding the sun and stars for days at a time? The Norse sagas hint at their secret weapon, a mysterious object known as a solarstein, a sunstone. This was no mythical artifact, but a sophisticated optical tool, a crystal that allowed these legendary explorers to literally see the invisible and measure their position on the globe with a natural technology we are only now beginning to fully appreciate. The Viking Sunstone was almost certainly a piece of transparent calcite, a crystal known today as Iceland spar for its prevalence there. This material possesses a remarkable optical property called birefringence. When a ray of light enters the crystal, it splits into 2 separate beams. This is caused by the way the crystal polarizes light. Even on a completely overcast day, a small patch of clear sky still emits polarized light, with its waves vibrating in a specific direction that forms a ring pattern centered on the sun's hidden position. A skilled navigator would hold the calcite stone up to the sky and rotate it slowly. At a certain orientation, the crystal's 2 images would appear equally bright, a visual cue that revealed the exact polarization pattern and, by extension, the bearing of the sun itself, even if it was well below the horizon. By taking multiple readings from different patches of sky, a navigator could triangulate the sun's location with astonishing accuracy, effectively creating a celestial compass from a piece of rock and a gray sky. This empirical mastery of optics gave the Vikings an almost supernatural edge in exploration. While other European sailors were largely confined to coastal hopping, terrified of losing sight of land, the Vikings could strike out across the open ocean with a profound confidence. This technology was a key enabler for some of history's most daring voyages: the settlement of Iceland in the 9th century, the colonization of Greenland in the 10th, and the legendary journey of Leif Erikson to the coast of North America around the year 1000 of the Common Era, nearly 5 centuries before Columbus. Their sunstone allowed them to measure not just direction but opportunity, turning the formidable North Atlantic from a barrier into a highway for their sleek longships. It was a tool that transformed weather from a navigational obstacle into a usable resource, finding guidance in the very clouds that blinded others. For centuries, the sunstone was dismissed as a mere legend, a fanciful element of the sagas with no basis in reality. That skepticism collapsed in 2002 with a stunning archaeological discovery. During the excavation of a 16th century English shipwreck, the Alderney, mariners found a clear, rectangular block of Iceland spar crystal lying near a pair of navigational dividers and other piloting tools. While the ship was later than the Viking Age, its context was undeniable. This was a navigational instrument. Then, in 2013, a team of researchers provided the definitive proof. They used a precise calcite crystal to take bearings under heavily overcast skies in northern Finland, and then calculated the Viking navigation route from Norway to a specific point on the southern coast of Greenland. The results were staggering. Using the Sunstone just once every 4 hours, even under complete cloud cover, their simulated voyage arrived with an error of less than 1%. This wasn't just plausible, it was proven to be exceptionally reliable, a method that could consistently guide a ship to within sight of its intended landfall after a voyage of over 1,500 miles. The true brilliance of the Viking Sunstone lies in its elegant simplicity and its profound demonstration of a different kind of science. The Vikings did not understand the quantum mechanical principles of light polarization. That explanation would have to wait for the 20th century. What they possessed was a deep, intimate knowledge of the natural world, honed through generations of observation and experimentation. They learned to read the subtle cues in the sea, the sky, the flight patterns of birds, and the behavior of light itself. The Sunstone was the pinnacle of this empirical tradition, a perfect fusion of a unique natural material and applied human ingenuity. It stands as a powerful testament to the fact that advanced technology does not always require complex machinery or theoretical formulas. Sometimes it is held in the palm of the hand, a crystal-clear window into the hidden workings of the universe, allowing a lone navigator on a wooden ship to measure a path across the ocean by finding a sun he could not see. From the foggy, empirical navigation of the Vikings, we now journey to the humid jungles of Mesoamerica, where an entire civilization constructed a universe out of time itself. We often think of the Mayan calendar as a single, ominous countdown to the year 2012, but this is a profound and tragic oversimplification. The reality is so much more magnificent. The Maya didn't have just one calendar. They wove together multiple, interlocking cycles of time into a grand, cosmic tapestry of staggering mathematical complexity. This wasn't merely a tool for marking days. It was the very beating heart of their civilization, a sophisticated metaphysical engine that measured everything from the growth of a corn plant to the orbit of Venus with a precision that still inspires awe today. The foundation of this system was a pair of endlessly turning gears, the Tzolk'in and the Hob. The Tzolk'in, or the Sacred Round, was a 260-day cycle composed of 20-day names combined with the numbers 1 through 13. Imagine two intermeshed gears, one with 20 teeth and one with 13. It would take 260 spins for a specific combination, like 8 Ajor, to come around again. This wasn't an arbitrary number. It corresponds to the length of human gestation, the growth cycle of corn, and even the appearance of the sun's zenith at certain latitudes. It was the rhythm of life itself, dictating the schedule of sacred ceremonies and the fortunes associated with each day, as interpreted by the community's timekeeping priests. Running concurrently was the Hob, a 365-day solar calendar of 18 months with 20 days each, plus a short, ominous 5-day period known as the Wayeb, considered a dangerous and unlucky time when the veil between worlds was thin. The Hob governed the agricultural year, the seasons, and the civic calendar, telling farmers when to burn their fields and when to expect the rains. But the true genius of the Maya was how they combined these two cycles to create a much larger, more precise unit of time. The Tzolk'in and Hob would only realign on the same day once every 52 years, a period known as the calendar round. This 52-year cycle was the cornerstone of Mayan historical consciousness, a grand generational marker that was cause for immense celebration and renewal. However, for recording history over longer spans, even this was insufficient. This led to their crowning achievement, the long count. This was a linear, rather than cyclical, way of measuring time, counting the days called K-in. From a mythical starting point, the Maya believed corresponded to August 11th, 3,114 years before the Common Era in our Gregorian system. The long count was a base 20 system, written in units of K in 1 day, Winal 20 days, Tun 360 days, Kayatun 200 days or about 20 years, and Bayactun 144,000 days or about 394 years. This allowed them to inscribe dates on their monuments with pinpoint accuracy for millions of years into the past and future, creating an unbroken, absolute timeline for their kings and gods. It was this system that reached the end of a major cycle, the 13th Bayactun, in December 2012, an event the Maya saw not as an apocalypse, but as a moment of profound cosmic renewal and transition. This architectural marvel of timekeeping was not built on superstition, but on relentless, meticulous astronomical observation. Mayan priest astronomers, working from observatories like the Caracol at Chichen Itza, tracked the movements of celestial bodies with a precision that rivals our own modern calculations. They calculated the solar year to be approximately 365.2420 days, and figure even more accurate than the Julian calendar used in Europe at the time. Their Venusian calendar was a masterpiece of predictive astronomy. They knew that Venus appears as both the morning and evening star, and they calculated its 584-day synodic period with such accuracy that their long-term prediction of its cycles had an error of just 1 day every 500 years. This was vital, as Venus was associated with the god Kukulkan, and its appearances were often tied to the timing of warfare and royal coronations. They also meticulously tracked the cycles of the moon, predicting eclipses, and understood the precession of the equinoxes over vast spans of time. Their calendars were, in effect, sophisticated mathematical models of the cosmos, running on a system of bars, dots, and the concept of zero, a mathematical breakthrough they mastered independently and used centuries before it appeared in Europe. To view the Mayan calendar system as merely a way to count days is to miss its entire point. It was the central organizing principle of their universe, a device that measured the sacred interconnectedness of all things. The movements of the stars were not separate from the planting of corn. The birth of a child was directly tied to the journey of Venus. The reign of a king was validated by its placement within the grand cycles of the long count. Time was not a linear arrow marching toward progress, but a sacred, layered fabric where the past, present, and future were in constant conversation. Their calendars were the loom on which this fabric was woven, blending astronomy, mathematics, theology, and agriculture into a single, coherent worldview. It represents one of humanity's most ambitious and successful attempts to not just observe the universe, but to truly measure its rhythm and find a meaningful place within its infinite turning cycles. While the Vikings mastered the art of reading the hidden sun, another legendary mind from antiquity was reputed to have commanded the sun itself as a weapon. Our journey now takes us to the shores of Sicily in the 3rd century before the Common Era, where the brilliant Greek inventor and mathematician Archimedes defended his home city of Syracuse against a massive Roman naval invasion. According to accounts written centuries later by authors like Lucian and Anthemius of Tralles, Archimedes did not just rely on conventional defenses. He is said to have engineered a device of terrifying simplicity and brilliance, an array of highly polished bronze shields or mirrors, arranged on the city walls and carefully angled to focus the intense Mediterranean sunlight onto the wooden hulls of the approaching Roman fleet. The concentrated beam of thermal energy would, in theory, generate enough heat to ignite the ships from a distance, turning the very light of the sun into a siege-breaking weapon. This is the legend of Archimedes Heat Ray, a device that, if real, would represent one of the most audacious applications of fundamental physics in the ancient world. The core scientific principle at work here is the parabolic reflector. By arranging a series of flat or slightly concave mirrors in a large, curved array, the individual rays of sunlight reflecting off each surface can be directed toward a single focal point. At that point, the cumulative energy of all those individual photons is concentrated into a tiny area, causing a massive and rapid increase in temperature, easily enough to char wood or set pitch-covered hulls ablaze. This isn't magic, it's a straightforward, if incredibly difficult to execute, application of optics and thermodynamics. The device wouldn't have measured light in a quantitative sense, but it would have measured human ingenuity's ability to harness a diffuse natural energy source and concentrate it into a potent, directed force. For Archimedes, a man who famously calculated pi, explained the principle of leverage, and designed revolutionary war machines like the claw that could lift ships from the water, such a feat seems almost par for the course, a logical extension of his profound understanding of geometry and physics. The historical validity of the heat ray has been fiercely debated for centuries. Skeptics raise several compelling practical objections. The ancient Greeks did not possess the technology to manufacture mirrors with the necessary precision and reflectivity. Bronze, even highly polished, reflects far less light than modern silvered glass and would tarnish quickly in the salty sea air, requiring constant maintenance in the middle of a battle. Coordinating a large array of mirrors held by soldiers on a wobbly seawall to maintain a steady focus on a moving ship hundreds of feet away would have been a logistical nightmare, if not an outright impossibility. Furthermore, the primary historical sources describing the siege, like Polybius, who wrote closer to the event, mention other fantastic Archimedes inventions like the claw, but make no mention of the burning mirrors, suggesting the story may be a later legend meant to burnish his already superhuman reputation. Yet the idea has refused to die, largely because modern scientific testing has shown the concept itself is not just plausible, but demonstrably effective. The most famous attempt was conducted by the Greek engineer Ioannis Sakkas in the 1970s. He enlisted 70 sailors, each holding a 3-by-5-foot polished copper mirror, and had them focus the sun's rays onto a wooden rowboat mock-up nearly 200 feet away. Within seconds, the boat burst into flames. The Mythbusters television show took on the challenge multiple times, initially declaring it busted when they failed with a small, static array. However, in a later special, they constructed a much larger array of over 500 mirrors on a single frame and managed to successfully ignite a wooden ship's hull at a significant distance, ultimately changing their verdict to plausible. These experiments prove that the fundamental physics is sound, the energy is there to be harnessed. The real debate, therefore, shifts from could it work to could the Syracusans have built and operated it effectively under siege conditions with 3rd century technology? Perhaps the most profound legacy of Archimedes' heat ray is not its historical truth, but its enduring power as a symbol. It represents the ultimate fusion of pure intellect and practical application, a mind so powerful it could weaponize geometry. It speaks to a vision of science not as an abstract pursuit, but as a direct force that could alter the fate of cities and defy empires. Whether fact or fable, the story has inspired centuries of scientists and engineers to explore the potential of concentrated solar power, a technology we are only now perfecting for sustainable energy. The heat ray measures more than just focal length and ignition temperature. It measures the incredible length of the shadow a single brilliant mind can cast across history, challenging us to distinguish between the limits of ancient technology and the boundless potential of ancient imagination. While the heat ray of Archimedes channeled the power of the sun for fleeting destruction, another ancient civilization perfected a technology that harnessed a far more fundamental force for enduring creation. In the vast, arid plateaus of ancient Persia, where the sun scorched the earth and surface water was a fleeting mirage, survival itself depended on a monumental feat of hidden engineering. Here, 1,000 years before the Common Era, Persian engineers began constructing one of the most sustainable and sophisticated water management systems ever devised, the Kanat. This was not merely a tunnel, it was a subterranean river meticulously measured and coaxed from the earth, a life-giving artery that allowed empires to bloom in the heart of the desert. The principle of the Kanat is one of elegant simplicity, but its execution required a breathtaking depth of geological and mathematical understanding. The process began with the identification of an alluvial fan at the base of a mountain range, where rainwater and snowmelt had seeped deep underground, creating a hidden aquifer. A master surveyor, known as a Mukani, would then determine the optimal path for the Kanat. His first and most critical task was to measure the precise gradient. The tunnel had to slope gently enough for the water to flow freely by gravity alone, but steeply enough to prevent siltation and stagnation. This gradient, typically a drop of just 1 meter for every kilometer of tunnel, had to be maintained with incredible accuracy over distances that could stretch for dozens of miles. A miscalculation of even a fraction of a degree could mean the water would flow backward or fail to move at all, rendering years of backbreaking labor utterly worthless. To achieve this impossible precision without theodolites or laser levels, the Mukani relied on a series of ingenious, low-tech surveying tools that were no less effective for their simplicity. His primary instrument was a large, water-filled basin called a mistaran. By ensuring the water's surface was perfectly level, he could establish a true horizontal plane from which to calculate his descent. He would then use a calibrated plumb bob and a wooden staff, marked in precise increments, to measure the vertical drop over a specific run of the tunnel. Some accounts suggest they also used a device called a kavat, a weighted, horizontal crossbar that could be aligned to confirm the tunnel's direction and slope. This was empirical engineering at its finest, a profound understanding of physical principles applied with simple, flawless craftsmanship to solve a problem of existential importance. The Kanat itself was the ultimate measuring device, its very existence a testament to the accuracy of their calculations. The construction was a Herculean undertaking that mobilized entire communities for generations. Work began by sinking a series of vertical access shafts, sometimes thousands of them, along the proposed route of the tunnel. These shafts served two vital purposes. They provided oxygen and light for the diggers, and more importantly, they allowed for the precise removal of spoil and the continuous verification of the tunnel's alignment and gradient from the surface. Teams of diggers working from the mother well at the aquifer end would then painstakingly excavate the horizontal tunnel, connecting the bottoms of these shafts. The knowledge required was immense. The Mukani had to understand soil mechanics to prevent collapses, hydrology to anticipate water tables, and ventilation to keep his workers alive in the stifling, dusty darkness. This was not digging, it was a form of subterranean architecture. The result of this colossal effort was nothing short of a technological miracle. A fully functional Kanat delivered a constant, reliable flow of cool, clean water directly from the aquifer to the surface outlet, called the Majar, without a single drop lost to the evaporating desert sun. This water was then channeled through surface canals to irrigate vast fields of wheat, barley, and dates, and to supply drinking water to cities and villages. The system was inherently sustainable. By tapping the aquifer directly, it prevented the over-extraction that plagues modern wells, and its gentle flow allowed for natural filtration, producing water of exceptional purity. The access shafts even served as natural cooling towers, creating microclimates that were used for cold storage, a prehistoric refrigeration system. The influence of the Kanat system rippled across the ancient world, a quiet testament to Persian ingenuity. The technology was adopted and adapted by countless cultures, from the Korres of China's Turpan Depression to the Fagara of North Africa. It is even argued that the Roman aqueduct, while more visually spectacular with its towering arches, was inspired by the functional principles of the Persian Kanat, albeit adapted for a different geography. The Kanat did not just measure water flow, it measured the height of a civilization's adaptation to its environment. It represents a philosophy of working with nature rather than conquering it, of using meticulous observation and measurement to unlock the hidden bounty of the earth. In an age facing our own water crises, these ancient tunnels, many of which still function perfectly today, stand as a silent, profound lesson in sustainable engineering, a legacy carved not in stone, but in the life-giving water that still flows through the dark heart of the desert. While the Persians were mastering the flow of water beneath the earth, the ancient Egyptians were perfecting the art of measuring the flow of time across the heavens, and they did so with an instrument of such elegant simplicity, it belies its profound sophistication. This was the Merkit, the instrument of knowing, a device that transformed the night sky into a grand cosmic clock. Imagine a priest astronomer on a rooftop terrace beside the Nile on a clear, ink-black night. In his hands, he holds not a complex machine of gears, but a humble forked palm rib, its top carved into a narrow slit. Hanging from this fork is a weighted plumb bob, a simple pendulum of string and stone. To the untrained eye, it is nothing, but in the hands of a master, this unassuming tool becomes a precision instrument for charting the very passage of the stars themselves. The operation of the Merkit was a beautiful blend of ritual and rigorous observation. The astronomer would position himself facing due north, using another instrument called a bay, a sighting tool with a narrow notch, to establish a perfect meridian line, an imaginary north-south line running directly overhead. He would then set up his Merkit so that the plumb bob hung freely, its weight creating a flawless vertical reference against the backdrop of the spinning cosmos. Now came the act of measurement. Through the narrow slit in the palm rib, he would carefully watch for a specific, bright circumpolar star, often one from the constellation we call Ursa Major, or the leg of the ox, as the Egyptians knew it. His task was to wait with immense patience for the exact moment that star crossed the meridian line he had established. The moment its light passed directly through his slit and aligned with the taut string of the plumb bob, he would call out, and an assistant would note the time on a water clock or clepsydra, which had been started at sunset. By tracking the transit times of a series of these Deccan stars throughout the night, they could divide the darkness into 12 equal hours, their length varying with the seasons but perfectly measured each evening. This was far more than an academic exercise. It was the very heartbeat of Egyptian civilization, a device that measured the sacred rhythm of their world. The primary timekeepers were the priests of the temple, and their observations dictated the timing of crucial nocturnal rituals meant to ensure the sun god Ra's successful rebirth each dawn, a daily victory over the forces of chaos. The hours marked by the Merkit told them the precise moment to make offerings, to recite spells, and to perform the ceremonies that maintained the cosmic order, or Mad. But its function extended beyond the temple walls. These precise astronomical observations were the foundation of the Egyptian calendar, one of the most accurate of the ancient world. By meticulously recording the heliacal rising of Sirius, the first day it became visible just before sunrise after a period of absence, they could predict the annual, life-giving inundation of the Nile with remarkable accuracy. This allowed the pharaoh's administration to prepare the entire country for the flood, coordinating the distribution of seeds, the mobilization of labor, and the logistics of the harvest. The Merkit, therefore, was a tool of both spiritual and state power, its measurements synchronizing the divine with the deeply practical. The true genius of the Merkit lies in its demonstration of a fundamental principle of ancient science, profound accuracy achieved through minimalist design. Unlike the Antikythera Mechanism's complex gear trains, the Merkit had no moving parts. Its precision was not engineered into its construction, but was instead outsourced to the universe itself. The Egyptians used the unchanging, predictable rotation of the celestial sphere as their clockwork, and the Merkit was merely a flawless reference point against which to observe it. This reflects a deeply empirical approach, a willingness to trust observable, consistent natural phenomena as the most reliable mechanism. It also speaks to a society with a sophisticated understanding of geometry and alignment, capable of conceptualizing and utilizing abstract lines like the meridian long before such concepts were formally defined. The plumb bob provided a perfect vertical, a fundamental reference drawn from gravity itself, while the sighting slit created an artificial horizon, allowing them to slice the sky into measurable segments. This simple combination turned the entire vault of heaven into a calibrated instrument. In the silent, star-filled nights along the Nile, the Merkit did more than just count the hours. It wove a continuous thread of knowledge, connecting the practical need to tell time with a grand philosophical desire to live in harmony with the universe's eternal cycles. It represents a moment where human curiosity, armed with nothing more than a sliver of wood and a hanging stone, reached into the cosmos and found a way to measure its majestic, turning dance. Earlier in our journey, we encountered the brilliant seismoscope of Zhang, the device that warned the Han court of a distant earthquake. But the sheer ingenuity of its internal workings deserves a much deeper exploration, revealing a mechanical mind that rivaled the greatest inventors of any era. The historical accounts describe a large, ornate bronze vessel, but the true magic was hidden within, a system so clever it feels centuries ahead of its time. While the exact mechanics remain debated, the most compelling reconstructions point to an inverted pendulum as the heart of the machine, a heavy mass suspended loosely from the top of the vessel, free to swing in any direction. This pendulum was the device's soul, its delicate sensor. The faintest tremor from a distant quake would cause this central mass to sway, but it wouldn't just shake randomly. Its movement would be a precise response to the direction and force of the initial seismic wave. This is where Zhang's genius truly shone. The swaying pendulum was connected to a series of intricate levers and arms, a hidden clockwork that acted as a mechanical brain. Each of the 8 dragons on the vessel's exterior was linked to this internal system. The design was calibrated with breathtaking precision. The lever mechanism was not a simple on-off switch, it was a discriminating filter. It was tuned to ignore the general, chaotic shaking that would follow a quake, and instead respond only to the initial, directional pulse of energy, what seismologists now call the P-wave. As the pendulum swung, it would put pressure on one specific lever aligned with the direction the wave came from. This pressure would trigger a release mechanism, unclenching the jaw of the corresponding dragon and allowing the bronze ball to fall into the mouth of the waiting toad below. The system didn't just detect vibration, it performed a primitive form of vector analysis, calculating the epicenter's bearing through pure mechanics. This was far more than a scientific curiosity. It was a vital instrument of statecraft deeply embedded in the Han dynasty's worldview. To the Han Chinese, the emperor ruled with the mandate of heaven, a divine right that required him to maintain harmony between the earthly realm and the cosmic order. Natural disasters like earthquakes were not random tragedies. They were interpreted as potent omens, potential signs of heavenly displeasure with the emperor's rule. Before Zhang Heng's seismoscope, such an event would be shrouded in fear and superstition, a crisis that could destabilize the entire empire if mishandled. The seismoscope changed this dynamic utterly. By providing an immediate, objective, and directional report, it transformed a mysterious act of the gods into a measurable natural phenomenon. It allowed the court to respond not with panic but with purpose. They could immediately dispatch officials and relief to the affected region, demonstrating the emperor's proactive benevolence and control. The device, therefore, was a powerful tool of political stability, using science to demystify the cosmos and reinforce the state's authority and competence. The legacy of this invention stretches far beyond a single warning in 138 AD. Its underlying principle, the use of a suspended mass to detect and measure ground movement, is the foundational concept behind every modern seismograph used today. While our instruments now use electronic sensors and digital readouts instead of bronze dragons, they operate on the same core idea Zhang Heng mechanized nearly 2,000 years ago. He had discovered a fundamental truth of physics and found an elegant way to embody it in bronze. The seismoscope stands as a timeless symbol of how the most profound technologies often blend abstract science with tangible art, creating an object that is not only functional but also beautiful, a testament to a civilization that saw no divide between engineering excellence and philosophical understanding. It measured not just the tremors of the Earth, but the tremors in the relationship between humanity and the powerful forces that shape our world. Imagine a Roman official tasked with planning a new road, a vital artery for trade and legions. He needs to know the exact distance between two cities to calculate travel time, resource costs, and strategic advantages. He doesn't rely on a soldier's guess or the inconsistent pace of a man counting his steps. Instead, he attaches a small, ingenious bronze box to the axle of a chariot. As the wheels turn, this device silently and mechanically counts every single revolution, converting the rotation of wood and iron into a precise numerical record of the journey. This was the Greek odometer, a masterpiece of applied mechanics that brought mathematical certainty to the vast, unmapped expanses of the ancient world. The principle was simple in concept but brilliant in its mechanical execution. Described in detail by the engineer Vitruvius in the 1st century before the Common Era, the odometer worked on a system of perfectly calibrated gears. A drive wheel connected to the chariot's axle would make one complete revolution for every time the wheel itself turned. This primary gear was then meshed with a series of other gears, each with a specific number of teeth, designed to reduce the massive number of wheel rotations into a manageable and countable output. The most common design used a worm gear, a screw-like gear that advanced a toothed wheel by a single notch with every full rotation. After a set number of revolutions, say 400, the distance of 1 Roman mile, the final gear in the sequence would complete its cycle. This action would trigger a release mechanism, causing a pebble or a small ball to drop from a hopper into a waiting metal bowl. The clear, audible clink of the stone was the sound of a mile being measured. At the end of the trip, the official simply had to count the number of stones in the bowl to know the exact distance traveled, a level of accuracy that was simply unattainable through any other means at the time. This was far more than a simple curiosity for wealthy inventors. The odometer was a powerful tool of imperial administration and military might. For the Roman army, logistics was the key to victory. Knowing the exact distance to the next water source, the next defensible hill, or the next enemy stronghold was crucial for planning marches, supply lines, and troop movements. A general equipped with odometer readings could predict the arrival of his forces with unprecedented accuracy. For the famed Roman road builders, the agrimensors, the device was indispensable. It allowed them to create those astonishingly straight, perfectly graded roads that still crisscross Europe today, placing milestones at exact intervals to inform and reassure every traveler. Furthermore, this data was the bedrock of cartography. The information gathered from countless odometer-equipped journeys across the empire was compiled to create the Tabula Peutingeriana, a vast map of the Roman road network that showed not just routes but the precise distances between stations. This transformed the daunting prospect of long-distance travel into a series of known, measured segments, making the empire feel smaller, more connected, and far more manageable. The existence of the odometer reveals a fascinating technological lineage. While Vitruvius, a Roman, described it, he credited the invention to the Greeks of the Hellenistic period, possibly even to the brilliant mind of Archimedes himself. This places its origins squarely in the same era of innovation that produced the Antikythera Mechanism. It shows that the same sophisticated understanding of gear trains and mechanical calculation wasn't just being used for modeling the cosmos, it was being applied to the most earthly of problems. The odometer and the Antikythera Mechanism are two branches of the same intellectual tree, one looking up to the stars, the other looking down at the road. This wasn't just engineering for engineering's sake. It was a reflection of a culture that valued precision, order, and the quantification of the world. The Greek odometer stands as a powerful, tangible link between the abstract world of theoretical mechanics and the dirt under the fingernails reality of building and governing an empire, proving that a journey of 1,000 miles truly did begin with a single, meticulously counted revolution. In the sun-scorched plains of Rajasthan, where the line between survival and surrender is drawn by water, ancient engineers devised a solution that was far more than a well. It was a subterranean cathedral of measurement, a breathtakingly beautiful machine carved directly into the earth. These are the stepwells of India, and structures like the 1100-year-old Chand Baori are not merely architectural marvels. They are intricate hydrological and astronomical instruments, designed with a precision that turned the struggle for water into a profound dialogue with the cycles of nature. With its 3,500 perfectly symmetrical steps descending 13 stories into the cooling darkness, Chand Baori resembles an inverted pyramid, a geometric void reaching into the heart of the water table. But every step, every platform, and every carving was a calibrated component in a grand device for measuring the most vital resource in an arid land. Primary function was, of course, water collection and storage, but the method was one of brilliant empirical observation. The stepwell's design was a direct response to the extreme seasonal fluctuations of the region. During the intense heat of the dry season, the water level would retreat deep into the earth, and the vast staircase provided access even at its lowest point. With the arrival of the monsoon rains, the water would rise, gradually flooding the steps from the bottom up. The steps themselves acted as a giant measuring stick, a clear visual indicator of the aquifer's health. Communities could literally read the water level on this architectural gauge, knowing precisely how many months of supply they had remaining based on the height of the steps submerged. This wasn't guesswork, it was quantitative resource management. Specific landings and wider steps at certain intervals often served as markers, indicating critical thresholds, the point at which rationing must begin, or the level that promised abundance for the coming year. The stepwell measured the community's future in increments of stone and water. This practical hydrology was seamlessly woven into a complex cosmological framework. The stepwell was not just a reservoir, it was a temple to the divine feminine, to the goddesses who governed water and fertility. The intricate carvings of deities, mythological scenes, and geometric patterns that cover every surface are more than decoration. Many scholars believe they encode calendrical and astronomical information. The play of light and shadow across these reliefs changes dramatically with the seasons. On the equinoxes or solstices, sunlight may fall at a specific angle to illuminate a particular statue or symbol, marking the turning of the year with celestial accuracy. The entire structure, often oriented with precise cardinal alignment, could have functioned as a massive sundial or a seasonal clock, its deep bowl casting shadows that moved predictably across the stepped opposite wall. This transformed the act of drawing water into a ritual aligned with the cosmos, a daily reminder that the monsoon rains were not just a weather pattern, but a sacred event tied to the movement of the stars. The true engineering genius of the stepwell lies in its passive sustainability. The deep, shaded structure created a remarkable microclimate. The temperature at the bottom could be as much as 10 degrees cooler than at the surface, drastically reducing evaporation loss, a critical measurement in itself for water conservation. The complex zigzag design and numerous pavilions also slowed wind speed across the water's surface, further preserving every precious drop. This was climate control achieved through geometry and thermodynamics long before the concepts were formally defined. The stepwell measured and mitigated the environmental forces that threatened its stored water, all without a single moving part or energy input beyond the initial brilliant design. In this way, the Indian stepwell stands as perhaps the most holistic ancient device we have encountered. It did not measure one single thing, but rather the intricate interplay between multiple systems, the hydrological, the astronomical, the seasonal, and the social. It provided a constant, tangible readout of the environment state, enabling a community to plan, to worship, and to survive in a challenging landscape. It is a monumental testament to a philosophy that saw no separation between the utilitarian and the spiritual, between engineering and art, between measuring the water below and the heavens above. These structures are a silent, stunning rebuke to the notion that sustainability is a modern invention, proving that the deepest wisdom is often found not in complex machinery, but in learning how to read the world itself. While the Indian stepwell was a monument to measuring and managing water in a single, sacred location, the Romans approached the challenge on a scale so vast it still defies belief, transforming the very concept of urban civilization. Their solution was not a single device, but an empire-wide network of liquid highways, the aqueducts. We often picture these structures as the iconic, soaring arches that stride across valleys, but that's merely the skeleton. The true genius, the living nervous system of this network, was hidden within a sophisticated, empire-wide system of flow control that measured, divided, and delivered water with a precision that would be the envy of many modern municipal systems. This wasn't just about moving water from point A to point B. It was about measuring its every drop and managing its force with an almost obsessive level of hydraulic intelligence. The journey began at the source, a pristine spring often located dozens of miles from the city. Roman engineers, using simple yet incredibly effective tools like the chorobates, a giant, water-leveled sighting board, would calculate the necessary gradient with painstaking accuracy. The aqueduct channel itself, the specus, was the primary measuring instrument. Its cross-sectional area was a known, fixed constant. By measuring the time it took for a float to travel a set distance down this smooth, cement-lined channel, engineers could calculate the flow rate, or quinaria, the fundamental unit of Roman water measurement. This was volumetric flow rate mastered 2,000 years before the formal mathematics of fluid dynamics were established, but the water's journey was far from a simple, straight shot. The network was a labyrinth of splitting and combining flows, and it was at these nodal points that their measuring technology truly shone. The key was the Castellum Aquae, or distribution castle, a massive water tower that served as the beating heart of the entire urban system. Here, the main aqueduct line would empty into a large, circular receiving basin. This was the central reservoir, but its purpose was more than just storage. It was the primary point of measurement and pressure regulation. Sediment would settle here, ensuring only clean water moved forward, but the real magic happened at the outlets. Arrayed around the sides of the Castellum were multiple secondary pipes or channels, each leading to a different part of the city: public baths, fountains, private residences, and industrial sites. The diameter of each outlet pipe was carefully calibrated to deliver a specific, predetermined fraction of the total incoming flow. This was distribution by design, not by chance. A larger pipe for the public baths ensured a massive, continuous flow for thousands of citizens, while a smaller one for a neighborhood fountain provided just enough for daily needs. This system wasn't just about volume, it was about pressure management. By elevating the Castellum high above the city, the Romans used gravity to create consistent, reliable water pressure for all districts below it. The calibrated outlets acted like a giant flow divider, ensuring that a wealthy patrician's villa on one hill couldn't monopolize the supply and leave a public latrine on another hill dry. This was hydraulic democracy engineered in lead and stone. Beyond the Castellum, the Romans employed a suite of other devices to measure and control their liquid treasure. Sluice gates, or cataracti, could be raised or lowered to precisely throttle the flow into different branches of the network, or to completely cut off sections for maintenance. But perhaps their most astonishing innovation was the accidental precursor to the Venturi effect. They observed that when water flowed through a deliberately constructed narrow section of pipe or channel, its velocity increased and the pressure at the constriction dropped. While they didn't have the mathematics to describe it fully, they applied this principle empirically. They used these constrictions in specific situations to increase the speed of flow and prevent sedimentation in critical sections, demonstrating a practical grasp of fluid behavior that was centuries ahead of its time. This entire network, from the gentle slope of the channel to the calibrated holes in the distribution tower, was a single, city-sized measuring device. It quantified not just water, but quality of life, public health, economic activity, and imperial power. The constant, reliable flow enabled the famous Roman baths, the sprawling latrines that supported dense urban populations, and the water-powered mills that ground grain for the legions. The aqueducts of Rome and places like Segovia were not just feats of architectural might. They were the ultimate expression of a civilization that believed even something as chaotic as water could be measured, mastered, and made to serve the greater good of the city. In a world where we equate technology with physical tools, gears, lenses, and compasses, the most sophisticated measuring device we may ever encounter exists not in metal or stone, but in the human mind itself. This brings us to the vast, sun-baked continent of Australia, where for over 60,000 years, Aboriginal cultures have utilized a system of navigation and knowledge so intricate that it redefines our very understanding of what a device can be. These are the songlines or dreaming tracks, a living, breathing library of the land encoded not in books, but in rhythm, melody, and story. Imagine a map you cannot see, but must hear and feel, a map that does not simply describe the world, but actively participates in its creation and maintenance through continuous performance. This is not a tool for measurement, it is measurement itself, woven into the very fabric of culture and consciousness. The genius of the songline system lies in its elegant fusion of geography and music. Each song is a meticulously crafted sequence of verses that corresponds exactly to the features of a specific journey across the country. The rhythm and cadence of the lyrics mirror the pace of walking, while the lyrics themselves are a dense, poetic catalogue of the landscape. A particular line might name a specific rock formation, describing its shape and spiritual significance. The very next line might encode the presence of a hidden waterhole, the type of soil underfoot, the stars that should be visible overhead at that point, or the animals that are likely to be encountered and when. Distances are not given in miles or kilometers, but in verses. To travel from a sacred mountain to a river valley might require the recitation of 120 precise verses, with the completion of the song coinciding exactly with arrival at the destination. The song becomes a living odometer, its stanzas measuring the land in units of cultural memory. This oral mapping technology served a purpose far beyond simple navigation. It was the foundational legal, historical, and ecological database for hundreds of distinct nations, a songline tracing the journey of an ancestral creator being, like the great rainbow serpent, would demarcate territorial boundaries, dictate law, and outline kinship and trading relationships between different groups. The songs were a form of intellectual property, a title deed to country, and an encyclopedic survival guide all in one. They measured seasons not by arbitrary calendar months, but by the flowering of specific plants, the breeding cycles of animals, and the movements of constellations, all meticulously recorded within the verses. This allowed for sophisticated resource management across a continent, ensuring that hunting and gathering were conducted sustainably and in harmony with the intricate cycles of the ecosystem. The land and the song were in a constant, reciprocal dialogue. By singing the country into existence, the people also cared for it, and by walking the country, they kept the song alive. The cognitive science behind this practice is as staggering as its cultural depth. The songlines represent one of the most effective and durable memory techniques ever developed by humans. By embedding vast amounts of practical, navigational, and ecological data into a rhythmic, melodic structure, the information is transferred from fragile short-term memory into robust long-term recall. The melody acts as a scaffold, the rhythm as a mnemonic trigger, and the physical act of walking the route while singing creates a powerful multi-sensory association between the body, the mind, and the landscape. This is the method of loci or memory palace technique, applied on a continental scale. The entire Australian continent becomes the palace, and every hill, river, and tree is a distinct locus holding a piece of vital information. This challenges the very core of Western technological bias, which often prioritizes external, material inventions. The songlines prove that the most advanced technology can be entirely cognitive, a system where the human brain itself is the processor and the cultural tradition is the operating system, updated and debugged over thousands of generations. The tragedy and the resilience of the songlines lie in their fragility and their strength. As a non-material technology, they are incredibly vulnerable to cultural disruption. Colonial settlement, the forced removal of people from their traditional lands, and the suppression of indigenous languages have severely damaged and broken many of these ancient tracks. A songline cannot be stored in a museum vault. It lives only as long as there are people to sing it and country to walk. yet their strength is their profound adaptability and enduring power. In contemporary Australia, there are ongoing, powerful efforts to reclaim and revitalize these songlines, not as relics, but as active, living systems of law, environmental management, and cultural identity. They stand as the ultimate testament to a different way of knowing, a different way of measuring our place in the world, not through separation and observation, but through intimate, sung connection. The songlines measure more than distance. They measure the depth of a people's relationship to their home, a continuous thread of knowledge stretching back to the very dawn of human history, reminding us that the first and most lasting technology is the story we tell. Our journey now plunges literally underground, into the very bones of a civilization that thought about water in a way no one else did for over a millennium. Far from the open oceans navigated by the Vikings or the celestial clocks of the Maya, we find ourselves in the labyrinthine basement of the palace of Knossos on the island of Crete, around the year 1700 before the Common Era. This is the world of the Minoans, and while their vibrant frescoes and mythical minotaur capture the imagination, their most enduring legacy might be what they built beneath their feet. A shockingly advanced, island-wide network of hydraulic engineering that didn't just carry water, it measured and mastered it with a sophistication that feels almost anachronistic. Walking through the complex, multi-story palace, you would have encountered wonders that would be the envy of any medieval European monarch 1,000 years later. Elaborate terracotta pipes, meticulously designed with a narrow end that fits snugly into the wider end of the next section, created sealed conduits that prevented leaks and maximized pressure. These weren't simple clay tubes, they were engineered components. Their tapered design was a deliberate innovation to control the flow of water, accelerating it to prevent sediment from building up and clogging the system, a principle still used in modern plumbing. These pipes snaked through walls and under floors, feeding not just utilitarian spaces, but luxuries that defined Minoan life. Beautifully tiled bathrooms with functioning latrines that could be flushed, elegant alabaster bathtubs, and stunning courtyard fountains that danced and sparkled in the Mediterranean sun. This wasn't just plumbing, it was hydraulic theater, a public display of a civilization's command over its most vital resource. The true genius of this system, however, lay in its unseen intelligence, the empirical calculations that made it all work. The Minoans were master hydrologists. They understood the critical importance of gradient long before the physics of fluid dynamics were formally defined. Using simple but effective tools like water levels and sighting poles, they surveyed the landscape for miles around, mapping the contours of the land with astonishing accuracy. They constructed massive aqueducts to bring fresh water from mountain springs, maintaining a consistent, gentle slope over long distances to ensure a steady, powerful flow into the palace complex. This precise control of gradient was their primary method of measuring and regulating water pressure. A slope too steep would create torrential, destructive force, while one too shallow would result in a pathetic, stagnant trickle. They found the perfect balance, engineering a system that delivered water with just the right pressure to reach the upper floors of their multi-story palaces and to make their fountains jet impressively into the air. But their control went even further. Archaeologists have discovered the use of stopcock valves made of stone or ceramic that could be rotated to open, close, or throttle specific water lines. This transforms the entire network from a passive conduit into a dynamic, manageable system. A custodian could isolate a single bathroom for maintenance without shutting down the entire palace's water supply. They could divert water to prioritize the kitchens during meal preparation or to a fountain during a ceremonial event. This ability to measure and manipulate the flow at will represents a quantum leap in urban planning. It meant water could be allocated based on need, conserved during shortages, and deployed for maximum aesthetic and practical effect. The Minoans weren't just channeling water, they were programming it, treating it as a measurable, distributable commodity. The purpose of this hydraulic marvel extended far beyond mere royal luxury. In a crowded, complex urban center like Knossos, public health was paramount. The sophisticated drainage system that ran parallel to the fresh water supply efficiently carried waste away from living areas and out of the city, mitigating the spread of waterborne diseases that would plague other ancient and medieval cities. This commitment to sanitation indicates a profound empirical understanding of the link between hygiene and health, a concept that would be largely forgotten after the collapse of their civilization. The constant flow of fresh water and the efficient removal of waste created a standard of urban living that would not be matched on such a scale until the height of the Roman Empire over 1500 years later. The silent, flowing testimony of the Minoan pipes forces a dramatic re-evaluation of this enigmatic culture. They are often portrayed through the lens of myth and art, a seemingly graceful, almost delicate society. But their plumbing reveals a different side, a people of profound practical intellect and rigorous engineering discipline. Their palaces were not just ceremonial centers, they were living machines powered by measured and controlled water. This technology highlights a civilization that valued comfort, health, and the mastery of the urban environment itself. It stands as a powerful, flowing reminder that a society's true sophistication is often best measured not by its grandest monuments, but by the quiet, reliable infrastructure that sustains daily life for all its citizens. What truly unites these 28 marvels across oceans and millennia is not just their bewildering complexity, but a shared DNA of human ingenuity that defies our tidy timelines. They are not random flashes of genius, but the products of a universal process, deep, sustained empirical observation. The Viking navigator didn't invent the polarization of light, he learned to read it in the sky. The Minoan engineer didn't create the principles of hydraulics, he observed how water flowed down a slope and harnessed it. These innovators were master naturalists, spending generations watching the stars track their paths, noting how certain metals resisted decay, and understanding how sound echoed in a sacred space. This wasn't science in the modern, institutional sense. It was an intimate, hands-on dialogue with the natural world, a relentless curiosity that measured, tested, and applied every observable phenomenon. This deep observation was always directed toward a purpose, answering a fundamental need that was both profoundly practical and deeply spiritual. The Roman Dodecahedron, whatever its true function, was a tool for imposing order, measuring distance for a road, or perhaps measuring celestial harmony for a ritual. The Mayan calendar was the ultimate fusion of the pragmatic and the divine, telling a farmer when to plant his corn and a priest when to summon a god, because in their worldview, these were two sides of the same leaf. The Indian stepwell was a community's lifeline, a quantitative water gauge, and a temple to the goddess of fertility all at once. These devices rarely fit into our modern categories. They existed in a world where understanding the flow of water was as sacred as understanding the flow of time, and where a compass could point both to a distant shore and to the center of one's spiritual universe. To achieve this, their creators consistently manipulated materials and mathematics with a sophistication that still staggers us. The Antikythera Mechanism's precise gear ratios, calculating the irregular orbit of the moon, represent a level of mathematical astronomy we simply didn't believe existed. The Delhi iron pillar's near-perfect phosphorus balance, creating a passive anti-corrosion shell, is a masterclass in empirical materials science. The Chinese south-pointing chariot's differential gear system is a feat of mechanical reasoning so advanced it feels out of place in its era. This points to a startling conclusion. These were not one-off miracles. They are the surviving evidence of robust, sophisticated traditions of technical knowledge, schools of thought, workshops of master craftsmen, and libraries of accumulated understanding that were every bit as advanced in their context as a modern research lab is in ours. And this is the core of the mystery that challenges our entire narrative of progress. The disappearance of this knowledge. The blueprint for Greek fire was so utterly lost that its formula remains a heated debate. The specific metallurgical art of the iron pillars creators was a peak that later Indian smiths could not consistently replicate. The vast intellectual framework behind the Mayan calendars was systematically dismantled and burned by colonizers. This pattern of loss and rediscovery suggests that technological advancement is not a smooth, ever upward climb, but a fragile and often broken chain. Civilizations rise, reach a zenith of understanding, and then collapse, taking their most profound secrets with them into the dust, leaving behind only cryptic fragments for later cultures to puzzle over, often having to reinvent the wheel centuries later. This forces us to abandon the comfortable, linear story of progress where we stand on the shoulders of giants in a neat, continuous sequence. Instead, we see a landscape of isolated peaks and hidden valleys. Human ingenuity is not a steadily brightening light. It is a series of brilliant, often disconnected flares in the darkness of history. The Antikythera Mechanism implies a whole Hellenistic world of geared technology that vanished in the fires of Roman conquest. The Baghdad Battery suggests a playful, experimental investigation into chemistry that may have been dismissed as a curiosity and forgotten. These devices blur the line between myth and science because they represent a science that was so advanced for its time that it literally became mythical to those who came after. Ultimately, these 28 wonders are more than just historical footnotes. They are a profound inspiration and an urgent caution. They urge us to look deeper into history, not as a primitive prelude to our own era, but as a rich source of alternative solutions and different ways of thinking. The sustainable hydrology of the Kanat, the cognitive mapping of the songlines, the passive cooling of the stepwell, these are technologies of profound harmony and efficiency that we are only now, in our age of ecological crisis, beginning to fully appreciate and desperately need to rediscover. They caution us that knowledge is not a permanent possession. It is a flame that must be diligently tended and widely shared, lest it flicker and die, leaving future generations to gaze upon our own greatest achievements as we now gaze upon the Antikythera Mechanism, with a mixture of awe, wonder, and the humbling realization that we are only just beginning to understand what they